Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. In the beginning, there is darkness, an infinite quiet, a velvet emptiness stretching beyond imagining. In that primordial silence, there are no stars, no light, nothing but the delicate hush before creation. Time itself hardly has meaning yet. The universe is newborn and opaque, a hot, dense fog gradually cooling after a furious birth. All is dark, all is still. Then, slowly, something stirs. A subtle whisper of light emerges from the depths of this darkness. It is faint at first, a mere trembling glow amidst endless night. This is not the light of a single star, but the combined radiance of a newborn galaxy, a sprawling city of stars igniting for the first time. In the cosmic womb of gas and dust, gravity has gathered matter into a luminous tapestry. Countless infant suns blaze forth together, piercing the cosmic night. A galaxy is born, and with it comes the dawn. This first glimmer is humble, yet it marks the end of the universe's long, dark ages. Out of chaos, form begins to take shape. The hot fog of creation has cooled enough for atoms to exist, for gravity to gently tug clumps of matter into tighter embraces. Within those clumps, pressure and heat awaken the first stars. They burn with a primal light, blue-white and brilliant, shedding the first illumination into the void. And as stars cluster by the hundreds and thousands, they weave the structure of the earliest galaxies. Imagine that moment, the darkness yielding to a faint patch of light hanging alone in a vast sea of black. This nascent galaxy, tiny and fragile, glows as a sign that the universe has entered a new epoch. It is a beacon of complexity emerging from simplicity. In its glow is the promise of everything that will follow. Every galaxy, every star, every planet, every living being. In that gentle cosmic dawn, one galaxy's light begins to shine, and the universe will never be the same. The birth of galaxies. From that first fragile beacon in the dark, the story of galaxies begins. In the aftermath of the Big Bang, the universe was an expanding ocean of hot, glowing plasma. As it expanded, it cooled. After about 380,000 years, matter and light could finally separate. Electrons settled into orbit around nuclei, and the brilliant glare of the young cosmos faded into a gentle afterglow. The universe went dark. For millions upon millions of years thereafter, there were no stars at all, just vast clouds of primordial hydrogen and helium drifting through a growing void. These were the cosmic dark ages, a time of silence and shadows, before the first galaxies, when the universe held its breath. Yet even in that quiet darkness, the seeds of galaxies were already there. The fireball of the Big Bang was not perfectly uniform. Tiny ripples in density, as small as 1 part in 100,000, permeated the early cosmos. These ripples were slight overdensities, faint imprints left by quantum fluctuations from the universe's first instance. As the universe expanded and cooled, gravity began to sculpt these ripples into something more. Wherever matter was a little denser than average, its gravity pulled surrounding gas ever so gently inward. Over tens of millions of years, those subtle clumps grew denser and denser, drawing in more material from their surroundings. Threads of gas began to spool into the denser knots. The once uniform cosmos developed a complex texture, a network of filaments and knots of matter, with growing voids in between. In the depths of those gathering clouds, pressure and temperature rose inexorably. Eventually, perhaps a couple 100 million years after cosmic dawn, the first fires lit. In the densest pockets of gas, gravity's squeeze ignited nuclear fusion. The first stars burst into existence, brilliant and short-lived, illuminating pockets of space that had never known light. These stars were unlike the stars we see today. They were monsters, dozens or hundreds of times the mass of our Sun, composed purely of primordial hydrogen and helium. They blazed hot and blue, pouring ultraviolet light into the dark cosmos. One by one, across the young universe, such stars flickered on, like sparks dancing in ashes. Wherever a cluster of these first stars formed, they collectively breathed life into a new galaxy. A proto-galaxy might have been small and ragged, just a diffuse clump of stars and gas bound by gravity, but it shone defiantly against the cosmic night. As more gas fell in, more stars kindled, and the proto-galaxy grew. The death of those first massive stars came swiftly and explosively. In a few million years, they lived out their lives and died in titanic supernova explosions. Those explosions, in turn, heated and stirred the surrounding gas, and for the first time seeded space with elements heavier than helium, carbon, oxygen, iron, and all the rest, forged in the stars' hearts. The ashes of those first stars mixed with pristine gas, enriching the cosmic clouds that would birth later generations of stars. In time, gravity drew small proto-galaxies toward one another. They merged and clustered, coalescing into larger assemblages. What began as chaotic clumps of matter started to take on structure. The pull of gravity and the conservation of angular momentum flattened some of the swirling gas into disks. Rotating systems of stars emerged, spinning faster as they accumulated mass. Over hundreds of millions of years, the universe transformed from an almost featureless expanse into a froth of newborn galaxies. The early galaxies varied in shape and size. Some were small, glittering crowds of stars, others more extended clouds of light. None were as large or organized as the majestic spirals that would come later. These were the seeds, the building blocks, still finding their form. As these first galaxies lit up, they also changed the very medium around them. The intense ultraviolet light from young stars began to ionize the hydrogen gas in intergalactic space, turning the cosmic fog transparent once more. The darkness between galaxies slowly gave way to a faint glow as space itself was rayonized, the second dawn after the first stars. The era of rayonization had begun, driven by the radiance of newborn galaxies and the quasars powered by nascent black holes in their hearts. By about 1 billion years after the Big Bang, this process was largely complete. The universe was filled with galaxies, large and small, shining and assembling into the grand cosmic structures we can still observe today. Thus, from the primordial chaos emerged the first galactic forms. What was once random and formless became patterned. Tenuous threads of gas and dark matter drew together. Stars ignited in clusters, and gravity molded the fire and smoke of creation into coherent islands of light. The birth of galaxies was not a single moment, but a gradual awakening, a transformation of the young universe from darkness into a vast cosmic garden seeded with the first galaxies. Those galaxies carried within them the echoes of the Big Bang and the first generation of stars. In their light, one could read the opening chapters of the cosmic story, how structure arose from chaos, how the simple gave rise to the complex. They were the first organized gatherings of matter on a colossal scale, precursors to the majesties that would follow. The galaxies had begun their long journey through time. The cosmic web. As the young universe continued to evolve, a grand pattern emerged on the largest scales. Galaxies were not scattered randomly like grains of sand. They were arranged along vast filaments of matter with enormous voids between them. What had begun as tiny ripples in density had grown into a cosmic web, a latticework of galaxies and gas stretching across the universe. Imagine a spider's web, or the neural threads of a mind, expanded to cosmic proportions. Hundreds of millions of light years long, these filaments are like the highways of gravity threading through space. Where filaments intersect, galaxies gather in greater numbers, building up clusters and superclusters. In between these luminous strands lie immense dark voids, regions spanning tens of millions of light years that contain hardly any galaxies at all, cosmic deserts separating the crowded cities of light. This is the cosmic web, the universe's large-scale architecture, a structure as delicate as lace, yet spanning unfathomable distances. Each galaxy is a point of light on a gossamer thread, part of a network that links it to its cosmic neighbors. If we could step back and see the universe from outside, the galaxies would trace filaments and sheets surrounding bubble-like voids. It would resemble a three-dimensional mosaic, with patterns repeating at scales far beyond any individual galaxy. The web is dynamic and evolving. Over billions of years, galaxies flow slowly along these filaments, drawn by gravity toward the dense junctions. Clusters grow at the nodes where filaments meet, as if nutrients were funneling along veins toward organs in a living creature. In this living lattice, matter streams from sparsely populated voids into the denser highways. The galaxies, like glittering beads, thread themselves along strings of dark matter. For it is largely the invisible dark matter's gravity that governs this vast design. The luminous galaxies merely illuminate the underlying scaffold, much as dew on a spider's web makes the otherwise invisible strands glisten in morning light. We see the galaxies and clusters, but beneath and around them is an even larger mass of dark matter, forming the backbone of the cosmic web. Together, visible and dark matter shape a universe that is not chaotic, but organized into this immense tapestry. The cosmic web is a beautiful paradox. It is nearly empty on the grandest scale, yet intricately patterned. Voids that span hundreds of millions of light years contain little but trace gases and the occasional lone galaxy, while thin filaments can carry chains of thousands of galaxies end to end. In a sense, the web connects all galaxies into one cosmic entity, a vast foam of matter and light. When we observe the distribution of galaxies in deep surveys of the sky, we find this striking order: clusters of galaxies clumped together, filaments bridging between them, and enormous voids where almost nothing shines. The universe has arranged itself into something like a cosmic honeycomb, each cell millions of light years across. This structure grew out of the faint blueprint of the early density ripples and has been expanding and evolving ever since. It is not static. Gravity continues to sculpt it, pulling filament strands tighter and draining the voids, even as the overall expansion of space stretches the web slowly over time. Yet on human timescales, it appears frozen, a snapshot of grand design. In the cosmic web, we find the context for every galaxy's existence. Each galaxy's story is threaded into this greater pattern. Just as a lone tree belongs to a forest, each galaxy belongs to the cosmic web, positioned in relation to all others by the unseen bonds of gravity. It is the universe's largest artwork, a web of galaxies, glowing softly in the dark, a structure so vast and ancient that it transcends any single galaxy, yet made up entirely of them. Anatomy of a galaxy. To understand a galaxy fully, we can zoom in from the cosmic web and examine the galaxy's own internal architecture. Each galaxy is a world unto itself, a vast assemblage of stars, gas, dust, and dark matter bound together by gravity. Consider a majestic spiral galaxy glimmering in space. What structures do we find within this stellar city? At the center lies the galactic core, a densely packed bulge of stars. Here, in this crowded hub, hundreds of billions of stars may be crammed into a region only a few thousand light years across. The core shines brightly with the combined glow of myriad suns, often with a warmer, golden tone from many old, evolved stars dwelling there. This central bulge is the ancient heart of the galaxy, a place of tight orbits and ancient starlight. Hidden deep within the core, often there lurks a supermassive black hole, the dark engine of the galaxy's nucleus. But from the outside, we mainly see a brilliant central swarm of stars. Surrounding this bulge, stars orbit in every direction, creating a rounded, ellipsoidal halo of faint light close to the center. Extending outward from the core is the galactic disk, a broad, flat plane like a giant carousel of stars. This disk can span tens of thousands, sometimes over 100,000 light-years in diameter. It is thin relative to its width, a cosmic frisbee shimmering with starlight. Within the disk, we see the graceful spiral arms. These arms wind out from near the center, like the slowly whirling arms of a cosmic pinwheel. They are not solid appendages, but sprawling patterns where stars and gas are slightly denser, like traffic jams of starlight. As such, they mark where stars are born. Along the spiral arms lie bright nebulae and clusters of hot young stars that light up the curving lanes. Massive blue stars, short-lived and radiant, trace the arms' shape, making them visible across space. The arms themselves rotate around the center, though the pattern rotates like a wave moving through the disk, even as individual stars travel their own orbits. Threaded through the spiral arms and the disk are dark ribbons known as dust lanes. These are vast clouds of interstellar dust and gas, the raw material for new stars. To our eyes, when we look at a galaxy edge-on or in detailed images, these dust clouds appear as obscuring bands that dim the light behind them. They weave through the bright starlight, giving spiral galaxies a mottled, feathered look. In silhouette against the galaxy's glow, dust lanes are the shadows of future stars. Within them, dense clumps will eventually collapse to form new suns. They also contribute to the galaxy's beauty, outlining the spiral structure in delicate detail. Beyond the visible disk and arms lies the galactic halo, an extended, roughly spherical realm that envelops the galaxy. This halo is sparsely populated with stars, but those it contains are among the oldest in the galaxy. Ancient star clusters, called globular clusters, roam the halo, each a tight ball of 100,000 or more very old stars. These clusters swarm like bees around a hive, orbiting the galaxy's center on paths tilted at all angles, oblivious to the neat rotation of the disk below. The halo's stars are so far flung that to an outside observer, the halo is a faint ethereal glow surrounding the bright disk, often visible only with sensitive instruments. Yet the halo holds more than just a few stray stars and clusters. It is also the domain of the galaxy's dark matter framework. Though invisible to any telescope, a vast halo of dark matter engulfs the entire galaxy and extends well beyond the visible stars. This dark halo is like an immense, hidden scaffold that gives the galaxy its gravitational weight. In fact, the majority of a galaxy's mass resides in this unseen component. It is this dark matter halo that keeps the fast-spinning disk from flying apart, providing the extra gravity needed to bind the outer stars to the galaxy. If we could see the dark matter, the galaxy would appear not as a discrete pinwheel of starlight, but as a great sphere of mass with a luminous disk shining at its center. All these components, the luminous core, the swirling disk with its spiral arms and dust lanes, the tenuous stellar halo, and the massive dark matter envelope, together form a single galaxy. They are bound in a complex, elegant dance. Stars in the disk orbit in orderly circles, while halo stars wander on more random trajectories. The core bustles with activity, crowded with stars, and likely a black hole at center, while the outskirts are quiet and thinly populated. Through it all, gravity choreographs each component. The entire galaxy rotates around its center, a grand rotation taking hundreds of millions of years to complete just one turn. The result is both dynamic and majestically stable, a cosmic ecosystem in which each part plays a role. When you gaze at a galaxy like our Milky Way or the Andromeda Galaxy through a telescope, much of this structure is hidden within the glow. But science has teased out the anatomy of galaxies by observing them in different wavelengths and by mapping the motions of their stars. We now understand that what looks like a simple hazy spiral in the sky is in fact an incredibly rich and layered system. Every band of light or shadow in a galaxy's image corresponds to one of these structural elements. The bright central bulge, the winding arms speckled with star-forming regions, the dark dust lanes, and the faint halo of ancient stars. These are the signatures of a galaxy's architecture. Each galaxy is a cosmic city with its downtown and suburbs, its outlying countryside of the halo, and its unseen infrastructure of dark matter that holds it all together. It is a marvel of self-organization. Billions of stars, each orbiting on its path, together creating the grand design we recognize as a galaxy. Types of galaxies. Not all galaxies share the elegant spiral structures of our example. In fact, galaxies come in a menagerie of forms, each type with its own character and history written in its shape. Astronomers classify galaxies into a few broad categories: spiral galaxies, elliptical galaxies, irregular galaxies, and lenticular galaxies. Each type can be thought of as a different personality a galaxy might possess, a reflection of its past and the environment in which it grew. Spiral galaxies are perhaps the most visually striking, grand cosmic pinwheels with curving arms. Our Milky Way is one such spiral, as is the famous Andromeda galaxy. Spirals have a central bulge and a flat rotating disk, with those characteristic arms unfurling outward. They tend to be rich in gas and dust, which fuels ongoing star formation in their spiral arms. The presence of bright young stars gives the arms a blue hue, while the central bulge often glows more yellowish with older stars. Spirals convey a sense of vitality and motion. Their very form suggests rotation and continuous creation. These galaxies often reside in calmer cosmic neighborhoods, small groups rather than huge clusters, allowing them to hold onto their gas and maintain their disk structure. Their history is usually one of relatively gentle evolution. They may have absorbed smaller companions over time, but they've avoided catastrophic collisions for billions of years, preserving their orderly disks. In mood, a spiral galaxy feels like a cosmic garden in bloom, full of stellar nurseries and varied ages of stars, structured yet dynamic. Elliptical galaxies, by contrast, are giant ellipsoids or spheres of stars with no disks and no arms at all. They range from nearly round balls to more elongated cigar shapes. An elliptical galaxy might contain hundreds of billions of stars as well, but it looks very different from a spiral. It is a smooth, diffuse glow of starlight, brighter toward the center and gradually fading outward, with little internal structure visible. The stars in ellipticals tend to be older, and new star formation is scant because these galaxies contain very little cold gas or dust. As a result, ellipticals often appear reddish or yellowish, since they lack the brilliant blue of young, massive stars. The mood of an elliptical galaxy is one of age and tranquility, or perhaps of spent energy. Many ellipticals likely formed from the violent merger of smaller galaxies. In those ancient collisions, their original disks and patterns were scrambled into a spheroidal swarm of stars. The tumult of a merger would have triggered bursts of star formation that consumed or expelled the remaining gas, leaving behind a relatively inert ball of stars. Thus, elliptical galaxies can be thought of as cosmic retirement homes. Their stars are old, their gas is gone, and not much new is happening within. Yet they possess a stately grandeur, often being the largest and most massive galaxies in the universe. Some, like the giants at the centers of galaxy clusters, outshine every other galaxy around them with their sheer population of stars. In their core, they may harbor extremely massive black holes, remnants of their dynamic youth, now dormant without gas to feed on. Then there are irregular galaxies, the misfits that defy simple shape classification. Irregular galaxies have no coherent structure, no symmetrical shape or central bulge that stands out. They are often chaotic assemblages of stars and gas, looking like hazy patches or distorted smears of light. Many irregulars are relatively small, perhaps early in their life or stunted by interactions. They typically have abundant gas and vigorous star formation, since their disorder often comes from gravitational disturbances that compress gas into new stars. When we see an irregular galaxy, we might be catching it in the middle of a gravitational tussle. Perhaps two galaxies are tugging at each other, or a past encounter has shaken one to pieces. Some irregulars are likely primordial fragments that never formed a neat structure. Others are former spirals that were torn apart by a close encounter with a larger neighbor. The large and small Magellanic Clouds, which are companion galaxies to the Milky Way, are examples of dwarf irregulars with active star-forming regions, giving them a ragged, lively appearance. The mood of irregular galaxies is youthful or turbulent. They can be thought of as cosmic nurseries, undergoing growing pains, their shapes unsettled but brimming with bright young stars and nebulae. They remind us that not all galaxies lead orderly lives. Some are constantly being reshaped by their environment. Finally, lenticular galaxies bridge the gap between spirals and ellipticals. A lenticular galaxy, classified as S0 in Hubble's tuning fork scheme, has a central bulge and a disk like a spiral, but notably lacks spiral arms. Imagine a spiral galaxy that has lost its sparkle. The structure is still a flattened disk, often with a lens-like shape when seen edge-on, but the youthful pattern of arms is gone. Lenticulars typically have used up or lost much of their interstellar gas, so new star formation has nearly ceased. Without young blue stars or pink nebulae to mark out arms, the disk appears smooth and featureless, populated mostly by older, reddish stars. In photographs, lenticular galaxies can resemble a fried egg, a bright yolk-like bulge and a thin white disk, but no feathered pattern on the disk. They often show prominent dust rings or lanes, indicating some remaining cold material spread in a ring structure rather than in active spirals. The evolutionary history of a lenticular galaxy might involve being stripped of gas, perhaps by the pressure of hot gas in a galaxy cluster, or by early bursts of star formation that exhausted the supply. Alternatively, a lenticular could be the product of two spirals that merged gently enough to form a disk, but mixed their stars thoroughly, wiping out distinct arm structures. The mood of a lenticular is intermediate, neither as active as a spiral nor as quiescent as an elliptical, a kind of cosmic middle age. They carry a sense of faded glory, as if we're seeing a once spiral galaxy that has quietly aged and settled down. These diverse galaxy types illustrate how environment and history shape cosmic destiny. A galaxy that grows in isolation with plentiful gas becomes a grand spiral. A galaxy that endures a violent collision may become an elliptical cinder. A small galaxy buffeted by neighbors might twist into an irregular form, while a spiral in a dense cluster might be stripped into a lenticular. There is also a continuum of subclasses between these main categories. Nature rarely draws sharp lines. But broadly, when we look across the universe, we see this rich variety. We see majestic spirals turning slowly in the cosmic dark, serene ellipticals glowing softly with ancient starlight, irregulars blazing with the fires of newborn stars amid their disarray, and lenticulars posing as remnants of spiral patterns long gone. Each galaxy, through its shape and color, tells a story of its life, its triumphs of starbirth, its calamities of collision, its feast or famine of gas, its youth and its maturity. In the sky's grand gallery of galaxies, every form is a chapter in the saga of cosmic evolution. Star formation, galactic ecology. Every shining star in a galaxy was once a spark struck in the darkness of a cold cloud. The birth of a star is a quiet yet profound event, taking place deep inside vast molecular clouds that drift in a galaxy's disk. These clouds of hydrogen gas and fine dust can span tens of light years and contain the raw material for thousands of stars. In the spiral arms of galaxies, such clouds are frequently nudged and compressed, perhaps by the passing ripple of a spiral density wave, or by the shock of a nearby supernova explosion, or by collisions with other clouds. Where the gas becomes densest, Gravity begins to take hold of it. Slowly, pockets of the cloud collapse inward under their own weight, gathering mass like snowballs rolling downhill. As a pocket contracts, its core grows hotter and denser until, at last, a critical moment arrives. Hydrogen atoms begin to fuse into helium, releasing energy. A star is born, lighting up the cocoon of gas around it. Stars rarely form alone. Dozens or hundreds can blossom within a single cloud, giving rise to a cluster of newborn stars. These sibling stars push away the remaining natal gas with intense starlight and stellar winds, carving out cavities in the cloud. In a matter of a few million years, a once dark nebula transforms into a glowing stellar nursery, a loose cluster of young stars surrounded by wisps of leftover gas, which shine in reds and blues under the onslaught of stellar ultraviolet light. The galaxy has spawned new light, and those new stars settle into orbit around the galactic center, joining the vast stellar population. Once born, a star lives by the light of its own fires. In its core, nuclear fusion converts lighter elements into heavier ones, producing the radiation that makes the star shine. A star's life is a constant battle between gravity pulling inward and pressure from fusion pushing outward. For most of its lifetime, millions to billions of years, these forces balance in a stable harmony known as the main sequence. The fate of a star and how long it shines depends almost entirely on its mass. The smallest stars, red dwarfs only a fraction of the sun's mass, burn their fuel so slowly they can live for trillions of years, outlasting any other objects in the galaxy. Medium-sized stars, like our sun, live for perhaps 10 billion years, steadily fusing hydrogen into helium and providing gentle warmth to any orbiting planets. The most massive stars, however, live fast and die young. A star dozens of times the sun's mass burns at ferocious rates, its core a cauldron fusing heavier and heavier elements in quick succession. Such a behemoth might exhaust its central fuel in only a few million years, swelling into a brilliant blue-white supergiant before its life reaches a dramatic finale. When a star nears the end of its life, the balance it maintained begins to falter. A sun-like star, once it has fused most of its core hydrogen into helium, will expand into a red giant, its outer layers puffing out and cooling even as its core contracts and heats further. In those red giant phases, the star may fuse helium into carbon and oxygen. Eventually, though, a star of that size cannot continue fusion forever. It sheds its outer layers in a gentle but spectacular event, creating a glowing shell of ionized gas called a planetary nebula. The core that remains becomes a white dwarf, a hot, dense ember roughly the size of Earth, slowly cooling over billions of years. In contrast, a massive star meets a more violent fate. Once its core has forged iron, an element it can fuse no further to gain energy, the core collapses under gravity in an instant, and the star detonates as a supernova. In that explosion, the star's outer layers are hurled into space at tremendous speeds, and for a brief time the dying star can outshine an entire galaxy. All that remains of the core might be a neutron star, an ultra-dense ball of neutrons only a dozen kilometers across. Or if the star was massive enough, the core collapse continues into a black hole. These deaths are not an end so much as a transformation. When stars die, whether by gentle puffing or cataclysmic blast, they return their substance to the galaxy. The material expelled, carbon, oxygen, nitrogen, silicon, iron, and a menagerie of elements, mixes back into the interstellar gas. A supernova explosion, in particular, enriches the surrounding nebula with the heavy elements once locked in the star's heart. The next generation of stars will condense from gas that is slightly more enriched, containing the ash of previous stars. In this way, each stellar generation seeds the galaxy with new elements, gradually changing the chemistry of the cosmos. In the earliest galaxies, the first stars contained only hydrogen and helium. Now,
After billions of years and countless stellar lives and deaths, galaxies are threaded with elements that can form planets, oceans, and life. Every atom of calcium in our bones, of iron in our blood, of oxygen we breathe, was forged in ancient stars and blasted into space by stellar death throes. The galaxy is continually being fertilized by its dying stars. Star death is often also a trigger for new star birth. The shock waves from supernovae can plow into nearby clouds, compressing them and kickstarting collapse. Even the winds from massive stars or the expanding shells of planetary nebulae push gas around, nudging some regions into gravitational instability. Thus, a kind of feedback loop exists. Stars form, they shine and shape their surroundings, and when they die, they jolt the galaxy's gas, sometimes inducing fresh stars to form. Meanwhile, stellar remnants like neutron stars or black holes remain as ghosts of the once bright stars, often invisible unless they interact further. For instance, a neutron star might later merge with another, creating a brief, brilliant event and forging the heaviest elements like gold. This cyclical flow of matter, from gas to star to gas again, is the engine of a galaxy's evolution. It is often referred to as the galactic ecosystem or the galactic recycling program. Just as in a forest, the death of old trees returns nutrients to the soil for new growth. In a galaxy, the deaths of stars enrich the galactic medium for new stars to grow. Over time, this process changes the galaxy. It might slowly alter the color of the starlight as generations shift from blue to golden. It builds up complexity in the chemical makeup of the gas. It populates space with exotic remnants. A galaxy continuously renews itself through its stars, even as it also ages when star formation rates decline. In a spiral galaxy, one can envision giant stellar nurseries lighting up along the arms, while elsewhere, supernovae pepper the heavens like fireworks, all contributing their part to the cosmic cycle. In dwarf galaxies, one massive star's explosion might have outsized influence, blowing gas out of the small system or quenching further star formation temporarily. In large galaxies, many cycles overlap. At any given time, some stars are forming, others are dying in different corners of the galaxy. The result is a complex, self-regulating community of stars and gas. The galactic ecosystem binds generations together. The newborn stars of today bear the heritage of extinct stars from yesterday, and the elements forged in those newborn stars will someday be spread across space to nurture yet another generation. It is a continuous poetic flow of creation and destruction. Through this stellar alchemy, the galaxy transforms itself over eons, ensuring that from the debris of old stars, new light will always emerge. This is how galaxies sustain their brilliance over billions of years, by the lives and deaths of stars, each shining and then returning its essence to the cosmic cradle, again and again. Black holes and galactic cores. In the hearts of galaxies lies a deep and intriguing secret. Nearly every large galaxy harbors a supermassive black hole at its core. These black holes are dark paradoxes, objects of unbelievable density and gravity, yet often the key to some of the brightest phenomena in the universe. A supermassive black hole, SMBH, can contain millions or even billions of times the mass of our Sun, all crammed into a region smaller than a star. In a sense, it is the anchor of the galaxy's nucleus, a silent heavyweight lurking amid the bright swarm of stars in the bulge. Our own Milky Way, for example, hosts a black hole of about 4 million solar masses in its center, hidden behind veils of dust. We cannot see the black hole itself. By definition, it emits no light. But we observe stars orbiting an invisible point with incredible speed, betraying the black hole's presence. It is a calm giant now, a sleeping dragon in the heart of the Milky Way, but it profoundly influences its environment. In some galaxies, especially in the earlier universe or in rare active phases, the central black hole is not so quiescent. When a substantial amount of gas finds its way into the galaxy's center, perhaps funneled by a merger or by instabilities in the disk, it begins to spiral into the black hole, forming a whirling accretion disk. The friction and gravitational energy in this disk heat the infalling gas to extreme temperatures, causing it to blaze with intense light. Ironically, the region around a black hole can become one of the brightest spots in the cosmos. We call such an object an active galactic nucleus, and in its most flamboyant form, a quasar. The energy released by matter just before it plunges into oblivion can outshine the entire galaxy. A quasar in a distant young galaxy may pour out as much light as 1 trillion suns, powered by a supermassive black hole gorging on infalling gas. From near the black hole's poles, twin jets of charged particles can be shot out at nearly light speed, drilling through the galaxy and beyond, like incandescent beacons. These jets and the flood of radiation from an active core can extend far into space, sometimes creating lobes of radio-emitting gas larger than the galaxy itself. The presence of a supermassive black hole is not a mere curiosity. It appears to be intertwined with the life of the galaxy. Astronomers have found a surprising correlation. The mass of the black hole in a galaxy's core is closely tied to the mass of the galaxy's central bulge of stars. This suggests that galaxies and their central black holes grow together, each influencing the other. How might this influence play out? Consider the black hole in its active phase. As it devours matter, it releases prodigious energy into the surrounding galaxy. This energy can heat or push away the galaxy's gas reservoir. In fact, powerful outflows driven by an active nucleus might sweep gas out of the galaxy's central regions or prevent it from cooling to form new stars. A single outburst from a feeding black hole can send shockwaves through the galaxy's interstellar medium, like a stone dropped in a pond. If too much gas is expelled or heated, star formation in the galaxy can slow down or cease, effectively quenching the galaxy's growth. Thus, the black hole acts as a cosmic regulator, sometimes curbing the very process that allowed it to feed. On the other hand, black holes can also be nurturing in a roundabout way. The tumult they cause might trigger starbirth in some cases by compressing gas in outlying regions, or later, as their jets fade, the enriched gas might rain back into the galaxy, ready to form new stars. The relationship is complex, a feedback loop that can both create and destroy. But clearly, the black hole is no passive passenger. It is an engine that can drive galactic evolution. Even in their quiescent state, these black holes contribute to the galaxy's gravitational potential, though for a large galaxy, the black hole's mass is a small fraction of the total. It's within the central few light years that the black hole dominates, governing the orbits of stars in the innermost nucleus. Beyond that, the broader mass of the galaxy takes over. Yet through episodic outbursts, a black hole's influence can reach far beyond its gravitational grasp. Imagine a galaxy in its youth, undergoing a merger with a neighbor. The disturbance funnels torrents of gas to the center. The black hole awakens, feeding voraciously. For a few million years, the galaxy becomes a beacon, an active quasar lighting up the cosmos. Its once dark core shines with overwhelming brilliance. Meanwhile, violent winds from the center blow out in all directions. In time, the fuel is spent. The black hole has cleared out its vicinity. The quasar dims, leaving a quieter galactic nucleus with less gas around. The galaxy enters a more gentle stage of life, perhaps transformed by the event. Maybe the once spiral structure has been scrambled, star formation has been truncated, and the galaxy will age into an elliptical form. At the center, the black hole, now bloated in mass from its feast, goes dormant again. But it remains ready, should new fuel arrive, to blaze forth once more. When galaxies collide and merge, eventually their central black holes do as well. Two invisible giants, drawn by fate, spiral toward each other in the merged core. They dance a gravitational dance, throwing off stars and energy, until finally, they coalesce into an even more massive black hole. This cosmic collision emits a burst of gravitational waves, ripples in space-time itself, that wash through the universe. For a brief moment, more energy can be carried away by these waves than in all the light of the observable universe. Though the event is invisible to telescopes, the fabric of the cosmos remembers it. The merged galaxy now has a new, heavier heart. In the everyday life of a galaxy, a supermassive black hole might seem to sit silently in the shadows. Yet its influence is always lurking in the background. In the motions of stars at the very center, in the periodic grand eruptions that can transform a galaxy's appearance, in the jets that can be detected far in intergalactic space, the presence of these cosmic heavyweights is felt. They are the storytellers of the galactic core, recording a history of feast and famine in the energy they release. Even in the cosmic web, where galaxies act as nodes, the most active galaxies announce themselves through the telltale signatures of their central black holes blazing. Thus, a galaxy's core is not just a dense cluster of stars, but often a stage for one of the universe's great dramas, matter confronting the abyss of a black hole. Through those encounters, tremendous power is unleashed, and the fate of the surrounding galaxy can be altered. The supermassive black hole, though occupying the tiniest fraction of a galaxy's volume, can govern the galaxy's destiny in remarkable ways. It is a fine illustration of how something very small in size can have an outsized influence, a single point of almost infinite gravity that helps steer the evolution of an island of 100 billion stars. In the cosmic tale, black holes are both destroyers and creators, keepers of galaxies' secrets, quietly coiled at the centers, awaiting the next act. Mergers and collisions. Galaxies are not isolated forever in the cosmic ocean. They drift and sometimes dance with one another, and when they meet, the encounter can be dramatic. Over the eons, gravity draws galaxies together, especially those bound in groups and clusters. When two galaxies venture close, their mutual gravity reaches across space like tidal fingers. Stars, gas, and dust in each galaxy feel the tug of the other. As a result, galaxies can interact in a slow gravitational waltz, swirling around each other, stretching and distorting in the process. If the encounter is gentle, a pair might simply swing by, perhaps swapping some gas or pulling out long streamers of stars, then part ways. But often, the dance becomes an embrace. The galaxies spiral in toward each other and eventually merge, combining into one larger galaxy. These mergers are transformative events, cosmic collisions that can reshape the structures and fates of the galaxies involved. Despite the word collision, when galaxies merge, their individual stars almost never collide directly. The distances between stars are so vast that they pass by one another like grains of sand in a wind-blown cloud. But the galaxy's overall structures are profoundly disrupted. As two galaxies interpenetrate, tidal forces shear off great swaths of stars and gas, flinging them into space. Elongated tidal tails unfurl from the merging pair, luminous streams of stars stretched out over hundreds of thousands of light years, arcing back like cosmic bridges. These tidal tails are beautiful evidence of the gravitational torment. What was once a neatly rotating disk might now sport long, curving appendages of scattered stars, or shells and ripples in the case of mergers that have nearly completed. Some stars and star clusters can even be completely ejected, cast adrift as intergalactic orphans. Gas, unlike stars, does collide in these encounters. When two galaxies merge, their vast clouds of gas slam into each other, lose orbital energy, and sink toward the center of the new union. This crashing of gas often ignites a frenzy of star formation, a starburst. In the midst of chaos, brilliant clusters of new stars ignite as the compressed gas yields fresh life. The cores of the merging galaxies may coalesce into a single, much brighter core. It's common for a merging pair to briefly become extremely luminous in infrared light, as dust-enshrouded starbursts and possibly an active central black hole heat the debris. The whole scene is one of both violence and creation. While gravity tears the old forms apart, it also triggers the birth of countless new stars. As time passes, tens of millions, then hundreds of millions of years, the two galaxies begin to settle into one. Their original identities fade as they share their stars and gas. The orbits of their stars become scrambled. If the merging galaxies were spirals, their majestic arms might be completely destroyed in the melee. In the aftermath, the remnant often takes the shape of a swollen, elliptical galaxy. Much of the orderly disk rotation is replaced by a more random swarming of stars. The gas, having largely turned into stars or been thrown out, is depleted. Star formation slows dramatically. The vibrant spiral galaxy thus may end its days as a quiescent elliptical, a kind of cosmic phoenix, reborn in a different form from the merger's ashes. Not all mergers are equal. Sometimes a large galaxy devours a much smaller one, a process poetically termed galactic cannibalism. The big galaxy's gravity simply rips the smaller apart, adding the smaller galaxy's stars to its own halo or disk and absorbing its gas. The victim galaxy might only announce its former presence through faint streams of stars left trailing within the larger galaxy's outskirts, or by a newly acquired outer shell of stars. Our Milky Way itself is in the process of cannibalizing several dwarf galaxies, even now. The Sagittarius dwarf galaxy, for instance, is being torn into a stream of stars wrapping around the Milky Way. The large and small Magellanic Clouds, our Milky Way's companion galaxies, are slowly surrendering gas, the Magellanic Stream, that will eventually rain onto the Milky Way, perhaps invigorating future star formation. In this way, big galaxies grow larger over time by eating their smaller neighbors. In dense clusters of galaxies, interactions are common and sometimes spectacular. High-speed encounters can warp galaxies or strip gas out of them without a full merger occurring, a process known as harassment. A spiral galaxy plunging through a cluster's hot intra-cluster medium might have its gas blown out, like leaves from a tree in a windstorm, quenching its star formation and converting it into a gas-poor, lenticular galaxy. Meanwhile, the cluster's central giant elliptical likely formed from the amalgamation of many smaller galaxies that fell to the center and merged over billions of years. The cluster environment is a grand ballroom where many galactic dances take place, some ending in mergers, others in fleeting touches that still leave marks. One of the most poignant aspects of galaxy mergers is that they are a key part of cosmic evolution. Small proto-galaxies merge to form larger ones in the early universe. Over billions of years, this hierarchical merging built up the massive galaxies we see today, and the process continues. Our own galaxy and Andromeda are on a collision course. In about 4 to 5 billion years, these two spirals will begin to clash. Over a few billion more years, they will likely settle as a single, much larger galaxy, perhaps a giant elliptical or a large disk galaxy with a totally new structure. In that distant future, the night sky for any surviving observers in the merged galaxy will be very different. No longer a view of a solitary Milky Way band, but a completely reconfigured firmament of stars. Yet, despite the violence, there is a grace to these interactions. We can think of merging galaxies as dancers in an ancient ballet, their motions governed by gravity's choreography. They approach, entwine, and eventually unite, their individual shapes subsumed into a new creation. In the process, they sow new stars and mix their stellar populations. The universe's grand design is partly written in these acts of union and transformation. Every large galaxy likely has a history of past mergers woven into its structure. Clues in the halo star distributions, shells, or rings that hint at long-ago meals. Even seemingly undisturbed spirals carry the genetic memories of smaller mergers that contributed to their growth. Galactic collisions remind us that the cosmos is dynamic and ever-changing. Over immense spans of time, galaxies will drift together and apart like drifting continents. No galaxy is an island entirely unto itself. Gravity connects them in an intricate web of encounters. From gentle tidal interactions that trigger spiral arm patterns to head-on collisions that destroy and remake, galactic interactions shape the universe. In their aftermath, new chapters of galactic life begin. What once were two distinct star cities become one, continuing the story now merged. In the silent ballet of galaxies, destruction and creation go hand in hand, a slow, stately dance that has been ongoing for billions of years and will continue as long as the stars shine. Dwarf galaxies, the small but numerous. Not all galaxies are grand spirals or giant ellipticals. In fact, the vast majority of galaxies in the universe are relatively small and faint. The dwarf galaxies. These diminutive galactic systems can be as little as a few thousand or a few million stars compared to the 100 billion stars of a galaxy like the Milky Way. Some dwarfs shine brightly with active star formation, while others are so diffuse and dim that they are barely distinguishable from a globular star cluster. They are the unsung populace of the cosmos, far more numerous than their larger kin and crucial to the story of cosmic structure. Dwarf galaxies come in various guises. Many are dwarf spheroidal or dwarf elliptical galaxies, little ovoid puffs of old stars, often found orbiting larger galaxies. These tend to have very low surface brightness, with stars spread out in a diffuse halo, and almost no gas or new stars. They appear as faint glows that one could easily mistake for mere star clusters, if not for their slight but telling differences, like the presence of dark matter. Other dwarfs are dwarf irregulars, small versions of irregular galaxies, often rich in gas and vigorously forming stars. The Large Magellanic Cloud and Small Magellanic Cloud, which companion our Milky Way, are examples of dwarf irregular galaxies, though on the larger end of dwarf status. They have blobby, asymmetric shapes and contain glowing nebula and young star clusters. There are also compact dwarf starbursts and ultra-faint dwarfs. The palette is broad. What unites them is simply their scale. They are tiny by galactic standards, ranging from a few hundred light-years across for the smallest ultra-faints, to perhaps a few tens of thousands of light-years for the larger dwarfs. In a sense, dwarf galaxies are the building blocks of bigger galaxies. In the early universe, much of the first generation of galaxies were likely small and clumpy, akin to dwarfs. Over time, many merged together to assemble the larger galaxies we see today. Those dwarfs that avoided being subsumed can still be found sprinkled throughout space. Large galaxies like the Milky Way and Andromeda are each surrounded by an entourage of dwarf satellites, relics of the assembly process and leftover pieces that haven't yet been consumed. Our local group, the cluster of galaxies including the Milky Way and Andromeda, contains dozens of these dwarf companions. Some orbit closely, repeatedly experiencing the tidal pull of their giant host, which can strip stars and gas from the dwarf and distort its shape. Others roam farther out, perhaps only loosely bound, or on their first infall into the group. Despite their small size, dwarf galaxies have an outsized importance in cosmic evolution. They are laboratories for star formation under conditions often quite different from those in large galaxies. For example, dwarfs often have lower heavy element abundances because they have not gone through as many cycles of starbirth and death, so their star-forming environments resemble those in earlier epochs of the universe. Studying dwarfs can thus give clues to how the first galaxies formed stars. Additionally, dwarf galaxies are the most dark matter-dominated galaxies known. In many dwarfs, especially dwarf spheroidals, the visible stars account for only a tiny fraction of the total mass. The rest is invisible dark matter that holds the dwarf together. This makes them key testbeds for our theories of dark matter and galaxy formation on small scales. The existence of ultra-faint dwarfs with only a few thousand stars hints that there might be numerous small dark matter clumps that only manage to gather a trickle of stars, potentially as fossil galaxies from the dawn of time. Dwarfs also illustrate what can happen to a galaxy in the presence of much larger neighbors. Some dwarf galaxies show clear evidence of past interactions, streams of stars being pulled off, telling us they are gradually being torn apart, or unusual bursts of star formation perhaps sparked by a close pass of another galaxy. Others have lost their gas entirely, possibly siphoned away by tidal forces or stripped by intergalactic plasma, leaving them stellar fossils with only ancient stars remaining. The smallest dwarfs are so feeble that even 1 or 2 supernova explosions might blow out most of their remaining gas, effectively stunting their growth. They walk a fine line between existence and dissolution, at the mercy of both internal tumult and external gravitational forces. In the larger narrative, dwarf galaxies might seem minor, but collectively, they are major players. They fill the filaments of the cosmic web more abundantly than big galaxies do, like tiny blossoms scattered among a few great trees. During big galaxy mergers, dwarfs are often the bystanders or the satellites that get tossed about or incorporated. And in the aftermath, some of the diffuse halo of a big galaxy consists of stars that once belonged to dwarfs, now dissolved. Every massive galaxy carries the heritage of dwarfs within it. One can imagine that if galaxies were characters in a story, the dwarfs would be the countless peasant villages to the great cities of spirals and ellipticals, humble and dim individually, but together forming the foundation of the galactic civilization. They quietly churn out stars in their little nurseries, or guard the ancient stars from the universe's youth, and sometimes sacrifice themselves to fuel the growth of their larger companions. Without dwarves, the universe's tapestry of structure would be incomplete. They are the glue holding the hierarchy together. Their subtle glow might be hard to detect, but it carries the whispers of the earliest times and the scaffolding of cosmic creation. In our own celestial neighborhood, the presence of dwarf galaxies reminds us that even around our grand Milky Way, there are smaller realms of stars in orbit, each with its own history. They may be faint, but they harbor clues to the formation of our galaxy and the nature of dark matter. As they dance attendance around the giants or wander the voids, dwarf galaxies continue to play out a vital chapter in the story of galaxies. The chapter of the little ones, the survivors, the building blocks that assemble and sometimes persist at the fringes of greatness. Globular clusters, ancient halo, denizens, scattered throughout a galaxy's halo like tiny swarms of fireflies around a great tree, are globular clusters, ancient congregations of stars that are among the oldest surviving structures from a galaxy's youth. A globular cluster is a tightly packed ball of stars, typically containing hundreds of thousands of stars gravitationally bound together in a sphere only a few dozen light-years across. These clusters hover in the outskirts of galaxies, orbiting the galactic center on paths that can be highly tilted or eccentric compared to the flat disk. They are fossils of the early universe, timeless wanderers carrying records of an epoch long past. The stars within a globular cluster are extremely old. Many formed when the universe itself was young. In the Milky Way, most globular cluster stars have ages of around 10 to 13 billion years, meaning they ignited not long after the first galaxies took shape. They are typically metal poor, containing only small traces of elements heavier than helium, which indicates they were born before such elements became common. Inside a globular cluster, stars are crowded together. In the core of a cluster, stars may be only a fraction of a light-year apart from each other, vastly closer than the nearest stars are to our sun. If you could stand on a planet inside a globular cluster, your night sky would be ablaze with thousands of brilliant stars, far brighter than any night sky view from Earth. Globular clusters have a distinct appearance, a concentrated, spherical glow that gradually diminishes outward, often with a bright core where the star density is highest. Through a telescope, they look like fuzzy balls of light, which resolve into myriad points toward the edges. They have evocative names like Omega Centauri, M13 in Hercules, or 47 Tucanae, each a glittering city of ancient suns. These clusters contain no young stars and almost no gas. Whatever gas they once had was long ago converted into stars or stripped away. As a result, globulars are not sites of ongoing star formation. Rather, they are stable, long-lived stellar systems, dynamically evolved over billions of years. Some have undergone core collapse, where the center became extremely dense. Some may harbor intermediate mass black holes in their cores, a subject of much research and wonder. In a galaxy like ours, there are on the order of 150 to 200 known globular clusters. Larger galaxies can have even more. Giant ellipticals often boast thousands of globular clusters, scattered in a vast halo around them, like a cloud of bees around a hive. The number and distribution of globular clusters tell a tale of a galaxy's formation. These clusters likely formed in the protogalactic fragments that later merged, or in the starburst conditions of a young galaxy. Some globulars might be the remnants of small dwarf galaxies that were consumed by the larger galaxy, their central star cluster surviving as a free-floating globular. For example, Omega Centauri in the Milky Way's halo is suspected to be the core of a long-ago captured dwarf galaxy due to its unusual size and multiple generations of stars. Thus, globular clusters can be thought of as either original building blocks or later acquisitions, but in any case, as very old family members of a galaxy. Globular clusters orbit in the galaxy's halo, and their orbits can take them far above and below the galactic plane. They slowly bob and weave through the galaxy's gravitational field, passing through the plane and back out again, like moths circling a flame. Over time, gravitational tides from the galaxy and even encounters with other clusters or massive gas clouds can tidally strip some stars from clusters, leaving streams in their wake. Indeed, some clusters have tidal tails of stars leaking out, contributing those stars to the general halo. But many clusters are robust enough to survive for eons, essentially unchanged, except for the gradual aging of their stars. The presence of globular clusters has been a key marker for astronomers trying to understand galaxies. In the early 20th century, the distribution of globular clusters in the sky was used to determine the Sun's position relative to the Milky Way's center. They formed a roughly spherical cloud pointing toward the true center of our galaxy. Today, globular clusters continue to be studied as clues to galaxy formation and chemical evolution. Each cluster is like a locked vault containing pristine samples of the conditions of the early galaxy. By examining their stars, we learn about the composition of the universe at the time and place those stars formed. In a more poetic sense, globular clusters are the jeweled inheritance of a galaxy, ancient treasures hanging in the halo, glinting with the combined light of hundreds of thousands of stars. They've seen the galaxy change and grow. They were already old when the Sun was born. As they drift silently in their wide orbits, they connect the modern galaxy to its primordial past. They are cosmic time capsules, preserving in their dense stellar populations a snapshot of the universe as it was billions of years ago. And every so often, when one passes overhead on a clear night as a faint, hazy spot in a telescope's view, we are reminded that high above the Milky Way's disk, these venerable star clusters keep their lonely vigil, like lanterns hung in the great dark hall of our galaxy's halo. Satellite systems, groups and clusters. Galaxies are seldom truly alone. They tend to gather in families, bound together by gravity into galaxy groups and clusters. Just as planets circle stars and moons circle planets, often smaller galaxies orbit larger ones, and clusters of galaxies revolve in a larger gravitational dance. In the cosmic neighborhood, one finds that most galaxies live as part of a system, be it a small group of a few members or a colossal cluster of hundreds. Through these associations, galaxies travel through space together, influencing one another's evolution. Consider our own situation. The Milky Way is not a solitary wanderer. It has a retinue of satellite galaxies. The large and small Magellanic Clouds are the most famous, but there are many others, some so small and faint they were only discovered in recent decades. These companions orbit the Milky Way, much as the Milky Way itself, along with the Andromeda Galaxy, M31, and a few smaller galaxies, all orbit a common center in what we call the local group. The local group is a collection of over 50 galaxies bound by their mutual gravity. At its heart are two giant spirals, the Milky Way and Andromeda, drawing closer to each other on a slow collision course. Around them are smaller galaxies moving in complex orbits, the entire group swaying in the gravitational field of its members. This little community spans a few million light-years across, an island of galaxies drifting together within the larger sea of the universe. Expand the scale further, and we find clusters, enormous gatherings of galaxies, where many such groups and individual galaxies have coalesced into an even larger system. The nearest large cluster to us, the Virgo cluster, contains some 1,500 galaxies, ranging from giant ellipticals to tiny dwarfs, all bound in a volume about 10 million light-years across. In clusters, galaxies swarm like bees in a hive, orbiting the cluster's center of mass. Often a huge elliptical galaxy sits near the center of a cluster, having grown fat on many past mergers, a sort of galactic monarch surrounded by a court of orbiting companions. These central dominant galaxies, sometimes called CD galaxies, can be the result of multiple galaxies merging right at the cluster core. The cluster itself is held together not only by the combined gravity of its galaxies, but also by a massive halo of dark matter and a hot, X-ray emitting gas that permeates the space between galaxies. Within this environment, individual galaxies move at hundreds or thousands of kilometers per second, their paths curved by the gravity of the cluster as a whole. Whether in groups or clusters, galaxies interact through gravity over billions of years. Smaller satellite galaxies weave around larger hosts in looping paths, occasionally being snared and absorbed as we've described. In groups like our local group, the pace is more sedate and interactions infrequent, but in a dense cluster, close encounters happen more often. A galaxy plunging through a cluster might have its gas stripped by the ram pressure of the intracluster medium or get tugged by multiple neighbors in succession. You can imagine a bustling city square where each galaxy is a person weaving through a crowd, some just brushing past, others colliding head-on. Over time, clusters tend to reshape their members. Spiral galaxies entering a cluster often lose their gas and transform into gas-poor lenticulars or ellipticals after enough interactions. The structure of galaxy systems is hierarchical. A small dwarf galaxy might orbit a larger spiral, like a sparrow flitting around an oak tree. That spiral, in turn, coexists with other galaxies in a group, a grove of trees bound by common roots of gravity. The group itself can be part of an even larger cluster, a forest of groves. And clusters themselves form parts of superclusters, sprawling complexes that are not fully bound, but still part of the same filament in the cosmic web. For example, our local group and the Virgo cluster are components of the Virgo supercluster, sometimes called the local supercluster, or even more inclusively, Laniakea, a vast region of space where many groups and clusters are somewhat linked by their motions. Traveling in these cosmic packs affects the fate of galaxies. Isolated galaxies, far from any others, might evolve relatively undisturbed for eons, their spiral arms and delicate disks intact. But a galaxy in a rich group or cluster lives in a more tumultuous environment. It has to contend with the gravitational pulls of neighbors, and it may find itself in tug-of-wars or near misses that distort its shape. It might feast on smaller satellites or be feasted upon by a larger neighbor. The presence of companions can trigger bursts of star formation, as when a small galaxy's gas is drawn out by a tidal encounter with a big galaxy and then funneled into new stars. Or conversely, can quench star formation, as when a cluster's environment strips a galaxy's gas away. Our Milky Way's own satellites illustrate a range of interactions. Some, like the Magellanic Clouds, are close enough that our galaxy's gravity is actively pulling streams of gas from them, and their orbits may eventually lead them to merge with the Milky Way. Others, like the dwarf Sagittarius, are already in the process of being assimilated, stretched into a long loop of stars. And Andromeda has its own satellites, and has cannibalized some, as evidenced by looping stellar streams in its halo. Meanwhile, the Milky Way and Andromeda together are bound in a dance that dominates the local group. The rest of the group's galaxies orbit this central pair, much like bees circling two large flowers. In the grand scheme, these groupings and satellite systems mean that galaxies are part of larger ecosystems beyond themselves. A galaxy's story is often inseparable from the story of its neighbors. They co-evolve, trading matter and gravitational energy. For astronomers, mapping the motions of satellite galaxies and group members is like charting the currents in a great cosmic archipelago. It reveals where unseen mass lies, dark matter binding the group, and pinpoints the future, like predicting the eventual merger of the Milky Way and Andromeda. Ultimately, the image of galaxies traveling in groups, each with its smaller companions in tow, underscores the interconnectedness of the cosmos. From our vantage point inside the Milky Way, we see the Andromeda galaxy as a faint smudge from Earth, our partner across space. And beyond it, we know countless other galaxies keep company with one another. In solitude, a galaxy would shine alone against the dark, but in reality, they move in clans and communities, their mutual gravity tying their fates together. In these communities, galaxies grow, interact, and sometimes merge, continuing the grand narrative of cosmic evolution, not as isolated actors, but as ensembles on the vast stage of the universe. The Milky Way, our home galaxy. From our vantage point on Earth, we are lucky to be inside a majestic spiral galaxy. The Milky Way, our cosmic home. On a clear, dark night, far from city lights, we can see it as a shimmering band of pale light arcing across the sky. This ghostly river of illumination is nothing less than the collective glow of billions of stars in our galaxy's disk, seen edge on from within. For millennia, humans have gazed at this Milky Way, named for its milk-like appearance, with wonder, not realizing until the last century that it is the cross-section of a vast star system surrounding us. Now we know. We live inside a grand galaxy, and everything we see in our night sky, every individual star, every nebula, is part of that galaxy, except for a few faint smudges that are other galaxies beyond our own. Imagine rising above our galactic plane to look down upon the Milky Way from afar. You would see a splendid spiral shape, about 100,000 light-years in diameter, with several graceful arms coiling out from a central bar and bulge. The galaxy would resemble a giant spiral seashell or a whirl of frost on a windowpane. The central region is a thick hub of stars, the galactic bulge, that appears as a yellowish oval in the heart of the spiral. Cutting through the bulge is a straight bar of stars, and from the ends of this bar, the spiral arms unfurl. These arms, with names like Perseus Arm and Scutum Centaurus Arm, wind outward through space, sprinkled with clusters of blue young stars and pinkish nebulae of glowing hydrogen gas. The Milky Way likely has 4 major spiral arms and some shorter spurs. Our Sun, a relatively unassuming star, resides in one of the minor spiral features, often called the Orion Arm or Orion Spur,
about 26,000 light-years from the galactic center. Out here in the galactic suburbs, we orbit calmly, taking roughly 230 million years to make one circuit around the center. The central bulge of the Milky Way is densely populated with stars, including many old red giants. Buried in the very core is a supermassive black hole, Sagittarius A, around which stars whip in tight orbits. Surrounding the disk and bulge, an invisible halo of dark matter engulfs the galaxy and holds it together. And within that halo orbit, the globular clusters and satellite galaxies we've mentioned. But to the eye, the Milky Way's most striking feature from within is the Milky Band of light. When you see that band, you are looking along the plane of our disk, through the thickness of stars and clouds. Dark patches within the band are not voids, but rather vast interstellar dust clouds that block the light of more distant stars. One such feature, the Great Rift, splits the Milky Way's band along the sky when seen from Earth. It is a series of dust lanes thousands of light years long that absorb starlight behind them, creating a dark divide amidst the glow. Our galaxy is a dynamic, rotating system. The entire disk is spinning. Stars and nebula orbit the center in orderly fashion. The Sun and its planets hurtle around the center at about 220 kilometers per second, carried along in the galactic rotation. Yet, because of the galaxy's immense size, this velocity still translates to an orbit period of roughly 250 million years. As the Sun moves, so too do all the stars around us, each tracing its path in the galactic gravitational field. It's a stellar metropolis in motion, though on human timescales the stars seem fixed in the sky. Within the Milky Way, all the processes we've described occur. Stars are being born in stellar nurseries, like the Orion Nebula. Massive stars are perishing in supernovae, as seen historically with events like the supernova of 1054 AD that created the Crab Nebula. Gas clouds are stirred and enriched by these events. Star clusters drift through the disk and halo, and our galaxy interacts with its neighbors. The Milky Way is currently pulling on the Magellanic Clouds, siphoning gas from them, and is busy cannibalizing the remnants of the Sagittarius dwarf galaxy. In a few billion years, it will feel the gravitational embrace of Andromeda. Our home galaxy is not a static backdrop, but an active participant in the cosmic dance. Culturally, the Milky Way has always inspired imagination. Ancient peoples called it the backbone of night, a pathway of souls, or spilled milk from the gods. These poetic notions hint at a truth. It is indeed a backbone of our existence, for it contains all the stars that gave birth to the elements we are made of, and all the stars that might be homes for other beings looking back at us. The Sun is but one star among the hundreds of billions in this galaxy, and our galaxy is but one among countless others, yet it is special to us because it is ours. Every atom in our bodies was forged in this galactic crucible, in stars that lived and died in the Milky Way. The iron in your blood might have come from a supernova in a long-gone star cluster, the calcium in your bones from another explosion in a different corner of the galaxy. To us, the Milky Way is enormous and encompassing, a vast city of stars in which we reside. When we gaze at the Milky Way band, we are looking into the structure of our home, seeing the combined light of distant suns woven together like a silvery ribbon. It evokes a feeling of both shelter and smallness. Shelter, because we are nestled in this cosmic city with its light surrounding us. Smallness, because we grasp that each tiny speck of that band is an entire sun, many with their own planets, and we are just on one of those specks. Yet there is also a sense of belonging. We are a part of this galaxy. We orbit its center, we share in its substance, and one day the atoms of Earth will recycle into the wider galactic medium. In a way, the Milky Way is not just our address in the universe, it is our extended body in cosmic terms. The air we breathe,
and the elements that form us were brewed in its stars. Our fate is tied to its fate. When eventually the Milky Way merges with Andromeda, our night sky will change, but life that might still exist then will continue under the umbrella of a new, larger galaxy formed from the two. The Milky Way's luminous band will fade and reconfigure, but the legacy of our home galaxy will carry on within that next cosmic generation. For now, on any given clear night, one can lie under the heavens and see the Milky Way's soft glow and remember that we live inside a marvel. We are moving through the quiet outskirts of a rotating spiral, a central black hole slumbering at its core, spiral arms gently turning with star formation, globular clusters hovering above like old witnesses. From the inside, we cannot see the elegant spiral form directly. That is left to our imagination and scientific inference, but we can sense its immensity. When we contemplate the Milky Way, we are both looking outward and inward, beholding the galaxy's splendor and reflecting on our own place within it. It is home, in the deepest cosmic sense, a vast starry home that cradles us and will continue to shine for billions of years, a beacon in the universe's darkness, marking where we come from. Andromeda and the local group. The Milky Way is not alone in the cosmos. Our grand spiral has a sister in the local group that is almost its twin in size and beauty, the Andromeda Galaxy. Andromeda, also known as M31, lies about 2.5 million light-years from us, so distant that its light takes millennia to reach our eyes, yet in the scale of the universe, it's right next door. On a clear autumn night in the northern hemisphere, one can spot Andromeda as a faint oval smudge in the constellation of the same name. What you are seeing with the naked eye is the combined glow of another galaxy's hundreds of billions of stars. Andromeda is a sprawling spiral, perhaps slightly larger than the Milky Way, with a bright central bulge and expansive spiral arms. It holds 1 trillion stars by some estimates, including many similar to those in our own galaxy. In fact, if one could view the local group from above, the Milky Way and Andromeda would appear as two hefty spiral galaxies cohabiting a region of space, with the smaller Triangulum galaxy, M33, as a possible third spiral orbiting nearby, and dozens of dwarf galaxies scattered around them like smaller islands in an archipelago. Andromeda and the Milky Way are bound together by gravity as the dominant members of the local group. They are on a slow but inexorable collision course. Right now, Andromeda is speeding toward the Milky Way at about 110 kilometers per second. Though that sounds fast, at intergalactic distances, it will take roughly 4 to 5 billion years for the two to meet. Our shared future is a cosmic rendezvous. These two great star swirls will collide and merge, reshaping both galaxies into a single new entity. In the lead-up to that event, over the next few billion years, the Andromeda Galaxy will gradually loom larger in Earth's night sky, assuming Earth still exists and has observers, growing from a faint patch to a magnificent elongated cloud of light as it comes closer. When the Milky Way and Andromeda finally collide, it will be an epic interaction like those we've described. The pair will likely pass through each other once or twice, throwing out tidal tails and triggering waves of star formation before ultimately coalescing. Simulations suggest that their central black holes will sink toward the middle of the merging system and eventually join in a colossal black hole merger. The end product of this dance is often nicknamed Milkomeda by astronomers, a giant elliptical or lenticular galaxy formed from the union of Milky Way and Andromeda. Most of the orderly spiral structure may be lost. The stars will settle into randomized orbits around the new galaxy's core. The night sky, as seen from within this future Milkomeda, will be different. Instead of the narrow band of the Milky Way, the entire sky might glow with a more uniform elliptical haze of stars, and many new star clusters and remnants of tidal tails could pepper the halo. During the merger, it's very unlikely that individual star systems will collide directly,
just as in other mergers, so our Sun and solar system might survive the smash-up relatively unscathed gravitationally. But their address in the galaxy could change significantly. The Sun could be flung into a new orbit, perhaps farther from the center in the merged galaxy, or conversely, drawn closer in. There is even a non-negligible chance the Sun could end up in a far-flung tidal tail, effectively cast into the outskirts of the new galaxy. Whatever the case, the stars of the Milky Way and Andromeda will mingle, and their histories will merge into one. Apart from the Andromeda Galaxy, the local group contains the Triangulum Galaxy, M33, a smaller spiral, about a tenth the mass of the Milky Way, that orbits not far from Andromeda. Triangulum may either join the collision, perhaps merging with the combined Milky Way-Andromeda system eventually, or remain as a satellite to the new giant galaxy. Then there are dozens of dwarf galaxies bound in the local group. Andromeda, like the Milky Way, has a system of dwarf companions such as M32 and M110, two of its brighter satellites, as well as a wealth of fainter ones found in recent surveys. Some of Andromeda's dwarfs show evidence of being torn by past interactions, just as ours do. The local group itself is a relatively peaceful little enclave, at the edge of a bigger structure. It is drifting in the outskirts of the Virgo supercluster, and being gently pulled toward the Virgo cluster's gravity, and even beyond, toward the Great Attractor region. For now, the local group's members are bound more strongly to each other than to any outside influence, which means that as the universe expands, our group will stay together while distant galaxies beyond our neighborhood recede from view over billions of years. The shared future of the Milky Way and Andromeda is a reminder that even galaxies have destinies shaped by gravity. These two have been drawing toward each other for eons, like two long-lost lovers on a collision course. In the cosmic perspective, 5 billion years is not so long. Our Sun might still be shining, though it will be nearing its red giant phase, and perhaps life will have found a way to endure or witness the merging of the skies. The event will not be sudden on a human timescale. It will unfold gradually across the ages, but the end result will be profound. The local group will effectively condense into a single, huge galaxy, surrounded by the remaining dwarf galaxies that didn't fall in. This new galaxy will become the only major galaxy in what used to be our local universe. For now, Andromeda remains a majestic galaxy in her own right, close enough to be studied in detail by our telescopes. We have observed its spiral arms, its dust lanes, its massive star clusters and nebulae. We've detected the orbital dance of its satellite galaxies and the presence of a supermassive black hole in its core. In many ways, studying Andromeda gives us a window into how an outside observer might view our Milky Way. It is like a galactic mirror, similar in structure and composition. Andromeda even has a halo of hot gas enveloping it, and streams in its outskirts that tell tales of devoured companions. Together, the Milky Way and Andromeda define the local group. Their mutual gravity defines the boundaries of our small corner of the universe. They are siblings and future partners in a cosmic merger. Our knowledge that these galaxies will merge adds a poignant twist when we look at Andromeda in the sky. We are looking at a future version of our own galaxy, in a sense. In that faint blur of light lies our destiny. Billions of stars that will one day swirl together with ours, ending the chapter of the Milky Way as a standalone entity and beginning a new chapter of a combined galaxy. It's a dramatic example of how even in the enormous timescales of the cosmos, change is constant and nothing remains isolated forever. The local group, with its two dominant galaxies and many smaller ones, is our cosmic neighborhood. It gives us context. We are part of a small cluster, a family of galaxies bound together. Within a few million light-years, all of our known galactic kin reside, sharing the darkness of space, engaged in subtle gravitational interplay that will eventually draw them together. When we contemplate Andromeda's approach and our shared future,
we come to appreciate that galaxies, too, have life cycles. They are born, they interact, they merge, and from those unions, new galaxies arise. And in that ongoing saga, we find both the history and the fate of our own starry home. Beyond the local, clusters, superclusters, and the Great Wall, stepping back even farther, our local group is just one gathering in a vast expanse of others. Our group is a suburb of the Virgo cluster's domain, and that in turn is part of an even larger arrangement. Galaxy clusters themselves are not isolated. They tend to cluster into superclusters and form immense filaments and walls on the grandest scales. The scale of these structures defies ordinary imagination. Take the Virgo supercluster, for instance, a region of space roughly 100 million light-years across that contains the Virgo cluster with its thousands of galaxies, our local group, and many other groups and clusters nearby. For decades, astronomers referred to this as our supercluster. It's as if all the galaxy clusters in our general vicinity are part of one gently held collection. But even that idea has evolved. Recently, scientists mapping the motions of galaxies discovered that the Virgo supercluster is part of an even larger entity, which they named Laniakea, Hawaiian for immeasurable heaven. The Laniakea supercluster stretches over 500 million light-years and contains about 100,000 galaxies, including those in Virgo and dozens of other clusters and groups. In this view, the Milky Way is on the outskirts of Laniakea, flowing along gravitational pathways toward a focal region near what's called the Great Attractor, a gravity hotspot that influences the motion of galaxies for hundreds of millions of light-years around. As we peer to still larger scales, the patterns become almost surreal, superclusters linking up in long chains and walls, interspersed with giant voids nearly empty of galaxies. One of the most famous of these colossal structures is the Sloan Great Wall, discovered in large galaxy surveys in the early 2000s. It is a vast filament of galaxies and clusters, a stupendous chain measuring about 1.5 billion light-years in length. Imagine a wall of galaxies stretching across billions of light-years. That is what the Sloan Great Wall represents. It's not a single coherent object like a wall of brick and mortar, but a concatenation of galaxy-rich regions forming a structure so large that it challenges our conception of uniformity in the universe. Other similar and even larger structures have been reported. The Shapley supercluster, a massive concentration of clusters about 650 million light-years away, is the largest overdensity of galaxies in our nearby universe. The so-called Hercules Corona Borealis Great Wall, hinted by distributions of distant cosmic explosions, might span over 10 billion light-years, though its exact nature is still debated. These names, Great Attractor, Great Wall, Laniakea, are our attempts to label features on the cosmic map of an almost ungraspable immensity. Between these filaments and walls lie the voids, enormous cavities where few galaxies dwell. One well-known example is the Boötes Void, an almost spherical region tens of millions of light-years across with only a handful of galaxies inside, earning it the nickname the Great Nothing. Such voids give the universe a foamy texture. The galaxies accumulate on the bubble's surfaces, the filaments and walls, and inside the bubbles are these voids. If we could view the universe on this scale, we'd see something like Swiss cheese or a sponge. The cosmic web we spoke of, with bright knots of clusters, elongated strands, sheet-like walls, and vast dark gaps. These immense structures are not fully bound by gravity. They are more like relic patterns, set up by primordial fluctuations and stretched by the expansion of the universe. Over billions of years, gravity has pulled matter into the dense zones, filaments, clusters, but the expansion of space itself is pulling those large-scale structures apart from each other. Our local group will stay bound and merge into a larger galaxy as discussed, but beyond that, many of the nearest clusters like Virgo will eventually slip away from our view due to the accelerating expansion driven by dark energy. In a far, far future,
An observer in what was once the local group, by then merged into a single galaxy, might see no other galaxies at all beyond its own, because distant clusters like Virgo will have receded beyond the cosmic horizon, effectively erased from the observable universe. But at the current cosmic epoch, we have the privilege of seeing the universe richly populated at all these scales. We can map the grand design, from our Milky Way's spiral arms to the local group's modest clutch of galaxies, to the Virgo cluster's swarm, to the Laniakea supercluster's flow, and onward to the great walls and voids. It's a nesting of structure within structure, a hierarchy that extends to the very edge of what we can observe. The cosmic web's largest threads and sheets are the stage on which the drama of clusters and superclusters plays out. Standing back to contemplate it, we recognize that our galaxy, though huge to us, is a tiny piece of this cosmic tapestry. The Sloan Great Wall, for instance, contains millions of Milky Way's worth of stars. And yet, even these titanic formations are just local quirks on the scale of the observable universe, which spans 93 billion light-years across. Zoom far enough out, and these filaments and voids themselves begin to blur into a picture of overall homogeneity. On the larger scales, the universe, with its countless galaxies and voids, looks the same in every direction, a testament to the uniformity of the Big Bang's aftermath. But the beauty is in the details. The local concentrations and patterns that emerged, like the great walls and superclusters, remind us that even a nearly uniform cosmos can paint itself into complex arrangements, given enough time and gravity. So beyond our local cosmic neighborhood, we find the architecture of the universe on its grandest scales. Galaxies collected into clusters, clusters into superclusters, superclusters into long filaments and walls bordering immense voids. It is a cosmic web so vast that light itself takes billions of years to traverse its length. These are the largest structures known, the chorus in which each galaxy is but a single voice. Our Milky Way's story is just one among billions, playing out in a quiet corner of Laniakea, which is one strand in the web. And as we survey this immensity, we come face to face with both the grandeur of creation and the humbling realization of how small our home is against the canvas of the cosmos. Dark matter, the invisible scaffold. Throughout our exploration of galaxies and the cosmic web, we've repeatedly encountered an unseen influence, something invisible yet massive, a dark scaffold holding galaxies together and weaving the universe's large-scale structure. This is dark matter, the mysterious, invisible mass that far outweighs all the normal matter we can see in stars and gas. Dark matter does not glow, does not absorb or emit light, and so we call it dark. But we know it's there by its gravitational pull, and without it, galaxies as we observe them would not make sense. One of the clearest signs of dark matter comes from the way galaxies rotate. In the Milky Way and other spirals, stars orbit the center under gravity's pull. If only the visible stars and gas provided that gravity, we would expect stars farther from the center to orbit more slowly, just as planets farther from the sun move slower, following Kepler's laws. But when astronomers measured the rotation speeds of stars and gas in the outer parts of galaxies, they found something astonishing. The outer stars were moving just as fast, or even faster, than those closer in. The rotation curves, plots of orbital speed versus distance from the center, stayed flat or rose instead of dropping off. This can only mean one thing. There is much more mass in the outer parts of galaxies than what we see. Some enormous halo of matter extends well beyond the visible disk, its gravity whipping those outer stars along at high speeds. This halo is dark matter, and it outweighs the visible galaxy by a significant factor. In the Milky Way, for example, estimates suggest that dark matter is perhaps 5 times more abundant by mass than all the stars, gas, and dust combined. Our galaxy is thus like a bright lantern embedded in a vast, transparent globe of dark matter.
Dark matter's presence was suspected even earlier in the context of galaxy clusters. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster of galaxies and found the galaxies were moving around so fast that the cluster should have flown apart, unless there was a huge amount of hidden mass providing extra gravity to hold it together. He called it Dunkel Materia, dark matter, and though his ideas were initially met with skepticism, decades later, the evidence piled up that he was right. Clusters of galaxies contain hot gas that emits X-rays, and by observing that gas, we can infer the cluster's gravitational pull. Again, we find that the visible galaxies and hot gas account for only a fraction of the gravity needed. Something unseen is making up the rest. Moreover, some galaxy clusters act as gravitational lenses, bending and distorting the light of more distant background galaxies. By mapping these lensing effects, scientists can weigh the cluster's mass distribution. The lensing maps clearly show massive concentrations that do not align perfectly with the visible matter, indicating dark matter clumps are present. Perhaps the most striking illustration came from observations of the Bullet cluster, a system formed by the collision of two galaxy clusters. When these clusters pass through each other, their clouds of hot gas, which constitute most of the normal matter by mass in clusters, collided and slowed down, whereas the galaxies, and presumably the dark matter, passed through relatively unimpeded. In X-ray images, we see the hot gas from both clusters piled up in the middle. That's the normal matter. But gravitational lensing maps show the bulk of the mass is offset from the gas, sitting where the galaxies have moved on. In other words, the dark matter of each cluster sailed through with the galaxies and is now separated from the normal matter. This dissociation is a dramatic confirmation that something unseen, dark matter, carries the majority of the mass and interacts differently, likely only via gravity, not collisions or electromagnetic forces. So what is dark matter? That remains one of the deepest mysteries in cosmology and particle physics. We know what it is not. It's not made of the same kind of atoms that make up stars, planets, and people. There aren't enough invisible atoms. Besides, such atoms would produce detectable radiation or absorption. Dark matter could be a new type of elementary particle, perhaps a heavy, slow-moving particle that barely interacts with normal matter except through gravity, often called a WIMP, weakly interacting massive particle. Despite numerous searches, deep underground detectors, powerful particle colliders, dedicated space observatories, we have not yet directly detected a dark matter particle. Another idea is that dark matter might be a whole sector of particles that are invisible to us, or something exotic like primordial black holes. For now, dark matter is known only through its gravity, like a ghostly presence felt but never seen. What we do know is that dark matter has been crucial in shaping the universe. In the early cosmic history, when matter began to clump, dark matter, being immune to light and radiation, could gather into dense regions before normal matter, which was coupled to light in the hot plasma of the young universe, could. These dark matter clumps acted as gravitational wells, pulling in ordinary gas once the universe cooled enough. They became the scaffolds where galaxies formed. Every galaxy sits in a cushion of dark matter. Every cluster resides in a much larger dark matter halo. In the cosmic web, dark matter forms the filaments and nodes, and regular matter simply follows, lighting up the structure with stars when it condenses enough. Without dark matter, the structures we see might not have formed as they did. Structures might be fewer and less clustered, because normal matter alone would have struggled to clump so quickly. We owe the richness of structure we see, in large part, to this dark, non-luminous mass. In galaxies today, dark matter governs the motions of stars in the outskirts and provides an invisible shield of gravity around the galaxy. It's as if each galaxy has an invisible companion much larger than itself, silently ensuring it stays bound and influencing its interactions. When galaxies collide, their dark matter halos pass through one another, like intermingling shadows, continuing to shape the gravitational landscape even as the visible portions entangle. Some scientists have proposed modifications to our theory of gravity as an alternative to dark matter.
suggesting maybe gravity behaves differently on large scales than we think. While intriguing, these modified gravity theories have difficulty explaining the full range of observations, especially things like the bullet cluster. The prevailing view remains that dark matter is real and made of something fundamental we have yet to identify. So we find ourselves in a universe where the majority of matter is of an unknown kind. About 85% of all matter is dark matter, with normal matter, like stars and gas, making up only about 15%. In terms of the total content of the universe, including energy, dark matter is roughly 27% of the universe, normal matter about 5%, and the rest, about 68%, is an even stranger component: dark energy. Thus, most of the stuff in the cosmos is invisible and exotic. And yet, despite being unseen, dark matter's effects are everywhere, in the gentle bend of starlight around a galaxy cluster, in the rapid whirl of a galaxy's outer rim, in the very existence of the Milky Way's thick halo of ancient stars. It is the universe's hidden framework, the silent partner to the visible cosmos. In our journey through galaxies, acknowledging dark matter adds a layer of almost mystical awe. We realize that when we gaze at a galaxy, the luminous spiral or ellipse is only the tip of an iceberg. Surrounding it is a much larger, dark halo that we cannot see, but that is very much there. In every direction around us, through that seemingly empty darkness of intergalactic space, dark matter forms an immense, invisible lattice. We live in a universe of light, immersed in a sea of darkness. And it is that darkness that holds the lights in its gravitational embrace. The galaxies shine as islands of starlight, but it is the ocean of dark matter that shapes the coastline of those islands. As our understanding deepens, the discovery of dark matter stands as a humbling reminder that the cosmos still guards profound secrets, with pieces of the puzzle missing from our view, yet undeniably real in their influence. Dark energy, the accelerating cosmos. As baffling as dark matter is, an even more enigmatic phenomenon dominates the cosmos: dark energy, the name we give to the force or influence that is accelerating the expansion of the universe. While dark matter pulls things together with gravity, dark energy seems to do the opposite, pushing the fabric of space apart. It's an unseen energy permeating space itself, and it accounts for nearly 70% of the total energy content of the universe. Its discovery in the late 20th century upended our understanding of cosmic fate and gave us a universe that, in the long run, is dominated by a mysterious, repulsive influence. The story of dark energy's discovery is one of subtlety and surprise. Astronomers in the 1990s set out to measure how fast the universe's expansion was slowing down. The universe has been expanding since the Big Bang, and it was assumed that gravity would be gradually decelerating that expansion over time. To measure the expansion rate in the distant past, two teams observed Type Ia supernovae, exploding stars that serve as standard candles in faraway galaxies. By comparing their brightness, distance, and redshift, a measure of how much the universe has expanded since the light left them, scientists expected to determine the rate of past expansion. The results came as a shock. The distant supernovae were dimmer than expected, implying they were farther away than our decelerating universe models predicted. Instead of slowing down, the expansion of the universe had sped up. At some point in the last few billion years, cosmic expansion started accelerating, and it's still accelerating today. To explain this cosmic acceleration, scientists resurrected a concept that goes back to Einstein's equations of general relativity, a term known as the cosmological constant, which Einstein originally introduced and later discarded as a kind of anti-gravity to hold a static universe in balance. Now, this cosmological constant, or something like it, was needed to account for the newfound acceleration. We call whatever is driving this acceleration dark energy. The word dark simply means we don't know its nature, much as with dark matter.
and energy suggests it's an inherent property of space. One interpretation is that dark energy is the energy of empty space, a vacuum energy that exerts a pressure causing space to expand. In Einstein's theory, a uniform energy field filling space can indeed cause a repulsive gravitational effect. Another way to think of it, imagine that every cubic centimeter of space has a tiny amount of energy, and as space expands, new space brings more of this energy into existence. So rather than dilution causing slowdown, it causes more push, a runaway effect. Our measurements of the cosmic composition, through multiple lines of evidence like the cosmic microwave background radiation and galaxy clustering, indicate that about 68% of the universe is this dark energy, 27% is dark matter, and only about 5% is normal matter. In other words, everything we see, galaxies, stars, planets, gas, is a mere sliver of what's out there. Dark energy is by far the biggest piece of the cosmic pie. Yet, we perceive it only indirectly, through the shape of cosmic expansion. The presence of dark energy has profound implications for the fate of the cosmos. With dark energy at the helm, the expansion of the universe isn't slowing, it's speeding up. This means that galaxies outside our local gravitational group are accelerating away from us at ever-increasing speeds. In billions of years, distant galaxies will slip beyond our horizon of visibility as they recede faster than light can reach us. Not that they move through space faster than light, but space itself expands and carries them away, effectively outrunning light. The universe will become emptier and darker on the grand scale. Trillions of years hence, cosmologists living in a galaxy like our Milky Way or its merged successor might see no trace of other galaxies or the cosmic background. The evidence of the Big Bang and the vast cosmos beyond would be hidden from them. Dark energy is driving the cosmos toward a lonely, cold future where each remaining bound structure, like a supergalaxy formed from a local cluster, is isolated in an expanse of growing darkness. The nature of dark energy remains one of the deepest questions in physics. Is it truly a constant property of space, Einstein's cosmological constant, which would mean the acceleration will continue at a steady rate forever? Or is it something dynamic, perhaps a field that changes over time, sometimes called quintessence in speculative models? If it were to strengthen in the future, one can imagine an even stranger fate, a big rip, where dark energy eventually overwhelms all bonds, tearing apart galaxies, stars, and eventually atoms themselves. Current data, however, are consistent with dark energy being a cosmological constant, a steady, unchanging push, implying an eternal acceleration, but not a catastrophic rip. In that case, the universe will asymptotically approach a state where every remaining galaxy cluster's cosmic neighbors are invisible beyond an immense gulf of expanding space. On human timescales, dark energy's influence is subtle. It doesn't affect the solar system or even our galaxy in any noticeable way. Gravity on smaller scales is far too strong. Dark energy's effects only become significant when you're looking across billions of light years of space. It's like a gentle pressure that you only feel over cosmic distances. But integrated over those vast expanses, it dominates. The combination of dark matter and dark energy in our universe is poetic in a sense. One holds galaxies together, the other drives them apart. They are two counterbalancing components shaping the cosmos. In the early universe, dark matter's gravity was the stronger influence, pulling matter into galaxies and clusters. But as the universe expanded and matter spread thinner, dark energy's relatively constant push came to dominate. And about 5 billion years ago, roughly when our sun formed, the expansion began accelerating. We live in a transitional epoch where dark energy is taking over. In the end, dark energy will win on large scales. The term dark energy itself evokes the mystery at hand. We are essentially invoking an unknown entity to explain our observations, a modern ether of sorts, though firmly grounded in evidence. It reminds us that there are fundamental aspects of reality we have only glimpsed. Just as dark matter revealed that most mass is invisible and of unknown form, dark energy suggests that even empty space carries a secret that governs the cosmos. In contemplating dark energy, we find the universe not only expanding, but doing so with a kind of silent urgency. The galaxies we chart today are like lights on an expanding balloon that's inflating faster and faster. And someday, many of those lights will be beyond our sight. It's a profound and somewhat melancholic realization. The universe is accelerating into darkness, and the splendid galactic tapestry we see now is, in a cosmological sense, ephemeral. Yet we are fortunate to exist at a time when we can still observe this tapestry and decode its messages. The discovery of dark energy is a triumph of human curiosity and ingenuity, showing that even in the twilight of faint supernova billions of light years away, we can read the cosmic runes and learn that something unseen is at work. As we add dark energy to our picture of the cosmos, our perspective shifts once again. The galaxies, those islands of stars, are being carried outward on a vast tide of space-time. Dark energy is that tide. We do not feel it directly, but on the largest scales, it steers the destiny of everything. In the grand story of galaxies, dark energy is the subtle chapter that comes late, changing the trajectory of all the characters towards an ending where distances become ever greater. It is a force of expansion written into the geometry of the universe itself, a whisper in the void that will in time dictate the final chapters of the cosmos. The future of galaxies. What lies ahead for galaxies in the deep future of the universe? Having traced their past and present, we now cast our minds forward to timescales almost beyond comprehension. The cosmic story is far from static. Galaxies will continue to change, collide, grow, and ultimately, perhaps, fade away as the universe ages. The processes at play now, from mergers to star formation, to the push of dark energy, set the stage for the far future. In the relatively near future, on cosmological scales, many galaxies will keep merging. Small galaxies will continue to be absorbed by larger ones, and even giants like the Milky Way and Andromeda, as we discussed, will coalesce into larger descendants. In galaxy clusters, successive mergers may result in one or a few supergalaxies dominating each cluster. We see hints of that already in places like the Coma cluster, where massive ellipticals sit at the center, products of previous mergers. Over the next tens of billions of years, this trend will continue. Cluster galaxies dance around each other, occasionally clashing and sticking together. Eventually, a typical galaxy cluster may condense most of its galaxies into one enormous elliptical galaxy, surrounded by a diminishing entourage of stragglers. Meanwhile, an even more inexorable process unfolds within galaxies, the slow but steady exhaustion of the fuel for star formation. Galaxies shine by virtue of their stars, and stars need gas to form. Right now, many galaxies still have supplies of gas, and in some, intergalactic gas from cosmic filaments continues to rain in, sustaining star birth. But this cannot last forever. Dark energy's accelerated expansion will thin out the infall of new gas from outside. Within galaxies, each generation of star formation locks away some gas in long-lived stars and in remnants like white dwarfs and neutron stars. Some gas is thrown out by supernovae and winds, but in many cases it escapes the galaxy or ends up too hot to collapse again. Bit by bit, galaxies use up or lose their reserve of cold gas. Star formation rates, already a trickle compared to their peak billions of years ago, will continue to decline. We can imagine the future of galaxies unfolding in several broad phases. First comes a stage of merger and growth. In the next tens to hundreds of billions of years, galaxies, especially within bound groups and clusters, will continue to merge into larger galaxies. Spirals will become ellipticals. groups will become single combined galaxies. The overall number of galaxies will decrease as they amalgamate. Next, a stage of starvation. As dark energy accelerates expansion and available gas is consumed or lost, galaxies will largely stop forming new stars. They will starve and age. Luminous young stars will become scarce, and the stellar populations will skew old and faint. After that, a degeneration stage. Over trillions of years, existing stars burn out. Galaxies turn into collections of remnants, white and black dwarfs, neutron stars, black holes, and very low-mass stars, if any remain. The light from galaxies will fade towards infrared and radio wavelengths, then into darkness as even the embers cool. Later, dissolution sets in. On fantastically long timescales, orbits within galaxies may decay or fling objects out. Black holes may dominate for a while, but eventually even they evaporate. If matter is unstable, the very remnants dissolve. Galaxies as gravitationally bound entities cease to exist in any recognizable form. And finally, an era of darkness. The universe is left with hardly any concentrated structures. Galaxies are effectively gone, and the universe becomes quiet and empty, save for the ghostly whisper of particles spread across unimaginable distances.
This is, of course, extrapolating physics far beyond what we have directly tested, so there is room for surprises or new physics along the way. But based on what we know now, the outlook is that galaxies have a finite era of active life. We happen to live in a vibrant time, about 13.8 billion years after the Big Bang, when galaxies are still shining and the cosmos is ablaze with starlight. In the distant future, the universe will be a far dimmer place. There is a melancholic grandeur in this projection. The galaxies we see, with all their stars and colors, are transient swirls in an evolving universe. Over immense timescales, the universe ages and the lights of creation wane. But one might also see it as a kind of cosmic life cycle. The universe alive with galaxies in its middle age will eventually enter its old age and retirement, its energy spent, resting in silence. Just as the night sky of a city might go dark as its lights turn off one by one, the cosmic city of galaxies will gradually darken as the stars wink out. Yet, this future is so distant that it vastly exceeds any human or even planetary timeline. For countless eons yet, galaxies will continue to shine and evolve. New stars are still being born today, and many generations of stars will yet live and die before the last lights go out. The legacy of the galaxies, the elements they've forged, the structures they've created, will persist, carried by the ever-expanding universe into whatever end state awaits. In contemplating the ultimate fate of galaxies, we come to terms with the finite nature of cosmic order, but we can also marvel that we, a form of conscious matter, are here now to witness and understand the galaxies in their glorious prime. We are observers in a universe that is brimming with activity, a universe that will, in the far future, quiet down. Understanding the future of galaxies adds a poignant final chapter to their story. From their fiery births in the early cosmos, to the gentle dimming of their lights trillions of years hence. It's a reminder that all things, even galaxies, and perhaps the universe itself, evolve and change, moving through phases from birth to maturity to an eventual quiet end. Observing galaxies. Eyes across the spectrum. Our understanding of galaxies has blossomed only because we have learned to observe the cosmos in ever more ingenious ways. Galaxies tell different chapters of their story in different kinds of light, and over the past century, humans have developed telescopes and detectors to catch every wavelength we can, from radio waves to gamma rays. Each portion of the spectrum offers a new eye on the universe, revealing phenomena we'd otherwise miss.
Observing galaxies across wavelengths is like listening to an orchestra with all its different instruments, rather than hearing just one. In visible light, the band of colors our eyes see, galaxies first appeared to us as faint smudges. Early astronomers with modest telescopes could discern the spiral shape of a few nearby nebulae like Andromeda, but their true nature wasn't known until the 20th century. It took larger telescopes and the work of astronomers like Edwin Hubble to show that these spiral nebulae were entire island universes far outside our own. By measuring Cepheid variable stars, Hubble determined Andromeda's vast distance, establishing that it was a separate galaxy. This was a revelatory moment. Suddenly, the universe became vastly larger, populated by myriad galaxies. With optical telescopes, we began to catalogue the shapes and populations of galaxies. We saw the grand spirals, the fuzzy ellipticals, the irregular patchy ones. We measured their rotations via Doppler shifts of their starlight, leading to the discovery of flat rotation curves and hence dark matter. We took spectra to learn their chemical compositions and ages of their stars. But galaxies emit much more than visible light. Consider the cold hydrogen gas in a spiral galaxy's outer disk. It emits radio waves at a wavelength of 21 centimeters. Radio telescopes can tune into this whisper from hydrogen atoms and map the extended arms of galaxies, often far beyond the optical edge. This is how we discovered that galaxies, like the Milky Way, have spiral arms stretching well past where the starlight fades, and that rotation stays fast out there, cluing us into dark matter. Radio astronomy also unveiled an entirely new type of galaxy, the radio galaxy, with colossal jets and lobes of radio emission extending millions of light years, powered by central supermassive black holes. These structures were invisible in optical light, but leapt out in radio maps. The radio sky showed that some galaxies had energetic phenomena we hadn't dreamt of. Quasars and active nuclei pouring out radio waves, pulsars and supernova remnants dotted within galaxies, and the diffuse glow of electrons spiraling in magnetic fields, synchrotron radiation, tracing where violent events had taken place. In the infrared, we open another window. Infrared light can penetrate dust that blocks optical wavelengths. When we peer at a galaxy in infrared, we see the glow of dust warmed by starlight. This allows us to peer into the dust-shrouded nurseries where stars are born. The center of our Milky Way, for example, is veiled by dust in visible light. But in infrared, the dense hub and the bar structure become clear, as do the populations of cool red stars in the disk. Infrared surveys discovered entire populations of starburst galaxies, galaxies undergoing intense, dust-enshrouded bouts of star formation, often triggered by mergers. These galaxies, like the luminous infrared galaxies, were practically invisible in optical, just dark, dusty shapes, but in infrared, they blaze brightly. The James Webb Space Telescope, working in infrared, can see some of the most distant, highly redshifted galaxies whose light has been stretched into infrared over 13 billion years of travel. With such eyes, we are now glimpsing the faint glow of galaxies formed just a few 100 million years after the Big Bang. Observations that were once purely theoretical dreams. Ultraviolet observations, on the other hand, highlight the hottest and youngest stars in galaxies. A spiral galaxy observed in UV looks different from the same galaxy in red light. The UV picks out the knotty regions of recent star formation in the arms, glowing with massive young stars and clusters. Satellites like GALEX, Galaxy Evolution Explorer, mapped the UV emission of galaxies, revealing extended disks of star formation and starburst activity in colliding galaxies. Ultraviolet light is also key to studying the behavior of gas in galaxies. For example, by observing the absorption of UV light from distant quasars by gas in intervening galaxies, we can trace the tenuous outskirts, the circumgalactic medium, of galaxies that would otherwise be invisible. X-ray telescopes, like NASA's Chandra or ESA's XMM Newton, opened yet another realm. In X-ray, we see the violent side of galaxies. In our own galaxy, X-rays come from neutron stars, and black holes in binary systems gobbling matter, from supernova remnants with shock-heated gas and from diffuse hot plasma. In clusters of galaxies, X-ray observations revealed vast pools of extremely hot gas, tens of millions of degrees, filling the space between galaxies, an ingredient of clusters that contains more normal matter than all the galaxies in the cluster combined. This gas glows in X-rays, and its distribution, often showing shock fronts or cavities blown by active galactic nuclei, tells the story of cluster mergers and black hole feedback. X-rays also pinpoint active galactic nuclei in other galaxies, often revealing the telltale energetic signature of matter swirling into a central black hole. Even relatively quiescent galaxies, like our Milky Way, have an X-ray glow from a halo of hot gas and from numerous faint X-ray sources, like cataclysmic variables and stellar remnants. Without X-ray astronomy, we would not know about the massive hidden gas reservoirs in clusters, nor the full energetics of black holes in galaxies. And then there are gamma rays, the highest energy photons, which can emanate from the most extreme phenomena. For instance, gamma ray bursts, likely from colossal stellar explosions or neutron star mergers, momentarily outshine entire galaxies, and some active galaxies have jets that produce high-energy gamma photons via shock acceleration of particles. The Fermi Gamma Ray Space Telescope charts the gamma ray sky, spotting the flickers of distant blazars and the diffuse glow of the Milky Way's disk from cosmic ray interactions. While gamma rays are less continuously associated with normal galaxy emission, they provide another piece of the puzzle for understanding cosmic particle accelerators and energetic transient events. Beyond the electromagnetic spectrum, we have recently gained a completely new way to observe cosmic events: gravitational waves. In 2015, LIGO detected the merger of two black holes by the ripples in space-time they emitted. As gravitational wave observatories improve, we might one day hear the mergers of supermassive black holes when galaxies collide, giving us a unique probe of those hidden central engines in the final dance. This would be a way of observing galaxies through the vibrations of space itself, complementing the story we get from light. Each wavelength and method of observation adds a layer to our understanding. We often combine them to get a complete picture. For example, consider a colliding pair of galaxies. Optically, we might see distorted star streams. In infrared, intense dust-obscured star formation. In radio, maybe a roaring central jet. In X-ray, a halo of hot gas or an active nucleus. And in UV, gleaming starburst knots. Only by putting all this together do we fully grasp the physical processes at play. Our telescopes have also extended our reach in terms of depth. The Hubble Space Telescope's deep field observations, where it stared at an apparently empty patch of sky for days, revealed 1,000 distant galaxies in that tiny speck, showcasing the universe's teeming population at great distances and thus great ages. This was like drilling a core sample through the cosmos, seeing galaxies from when the universe was a fraction of its current age. Now, with Webb, we push even further, seeing perhaps some of the first galaxies to have formed. On the other end of the scale, surveys like the Sloan Digital Sky Survey have charted the positions of millions of galaxies, making three-dimensional maps of the local universe's large-scale structure, literally mapping the cosmic web of galaxy clusters, filaments, and voids that we described. Observing galaxies isn't just about passive viewing. It's a detective story where we use all these clues: the light across the spectrum, the motions of galaxies, the shadows they cast by absorbing background sources, the gravitational lensing distortions, etc., to infer what's happening inside them and around them. We've developed techniques like spectroscopy to measure rotation speeds, chemical abundances, and even the spin of black holes via the broadening of emission lines. Long baseline interferometry links radio telescopes across continents to see fine detail in distant galaxy cores, resolving structures light years across in objects billions of light years away, an astounding resolution which gave us
For example, the Event Horizon Telescope's first image of a black hole shadow in the galaxy M87.
In essence, humankind has gradually taught itself to see the universe in all the forms of light that it offers. Each advance, the first telescopes, photography, spectroscopy, radio dishes, space-based detectors, has unveiled a new surprise about galaxies. And with each new observational tool, our mental picture of what a galaxy is has evolved. From the lone spirals quietly rotating, we learned about violent starbursts, powerful jets, hidden mass, dynamic evolution, all through the window of multi-wavelength observation. The story of galaxies has been revealed to us photon by photon, wave by wave. Where once our ancestors saw a milky band and a few fuzzy patches and wondered what they were, we now see an almost comprehensible panorama of structured islands in space, rich with detail and activity. But that comprehension continues to deepen with every new telescope launched or built. We stand now in an era where we can observe galaxies not only in their present glory, but also at the brink of their birth, and where we can survey the cosmic tapestry on scales that capture the grand patterns of the universe. Our telescopes are time machines as well as eyes. Because light takes time to travel, when we observe distant galaxies, we are seeing them as they were long ago. This means observing galaxies is also observing the history of the universe laid out in the sky. With each improvement in our observational reach, we push that history a little further back, closer to the first dawn of galaxies. And with each improvement in resolution and spectral range, we peel back another layer of the processes that make galaxies tick. From Galileo's first look at the Milky Way resolving into countless stars, to Hubble's leap in identifying galaxies beyond our own, to modern observatories mapping the very edges of the visible universe, our ability to observe has transformed the unknown into the known. Every detail we've recounted, from dark matter to black holes, from the spiral arms young stars to the halos ancient ones, from cosmic web structures to cosmic expansion, was gleaned through careful observation and clever inference. As we continue to develop new ways of looking, like future extremely large telescopes on Earth, next-generation space observatories, gravitational wave networks, neutrino observatories capturing cosmic events, we will surely uncover more about galaxies, perhaps phenomena we haven't even anticipated. The cosmos keeps offering up its secrets to those who look with curiosity and perseverance. In observing galaxies across all wavelengths, we have effectively learned the language in which the universe writes its autobiography. Each photon is a letter from the cosmos, and by collecting and interpreting them, we've read the epic of galaxies, an epic still ongoing, with chapters yet to be witnessed. Time travel. Looking back in time, one of the most astonishing aspects of observing galaxies is that it is akin to time travel. Because light does not reach us instantaneously, but has a finite speed, looking farther into space means looking further back in time. Every galaxy we observe comes with a built-in delay. We see it not as it is right now, but as it was when the light began its journey to Earth. For nearby galaxies, that delay might be a few million years. For distant galaxies, it can be billions of years. In effect, telescopes are time machines, allowing us to witness snapshots of the universe's history at different epochs. Consider our nearest large neighbor, the Andromeda Galaxy, at about 2.5 million light-years away. The faint glow we detect from Andromeda tonight set out from its stars 2.5 million years ago, when early hominins were roaming the African plains. In the intervening time, those photons traveled the intergalactic gulf and are only now hitting our eyes or detectors. So we see Andromeda as it was in the distant past, though on cosmic scales 2.5 million years is relatively small. If some catastrophe befell Andromeda in the last couple million years, we wouldn't know yet. Now stretch this idea further. The Virgo cluster of galaxies, about 50-60 million light-years away, appears to us as it was around the time dinosaurs went extinct on Earth. Light from galaxies at the edge of the observable universe, say 10 or 12 billion light years away, left those galaxies when the universe was very young, perhaps only 1/5 or 1/10 of its current age. In other words, we have images of galaxies from a time when they were newly formed, still in the act of building their first generations of stars. By looking at more and more distant galaxies, we effectively compile a series of cosmic fossil snapshots at different times after the Big Bang. Astronomers exploit this natural time machine effect to study the evolution of galaxies. We can observe galaxies at a range of distances, hence ages, and piece together how they change over time. For example, when we observe galaxies 10 billion light-years away, we might find that many are smaller, more irregular, or actively forming stars at a higher rate than typical galaxies of today. And indeed, surveys have shown that galaxies in the younger universe were often clumpy and actively merging, gradually assembling into the larger, more structured forms we see around us now. We see fewer big ellipticals and spirals when we look far back. Instead, we see their progenitors, little fractious dwarfs and colliding systems. We also see quasars blazing brightly in the distant universe, telling us that supermassive black holes grew quickly in the early epochs and then often quieted down by today. It's as if we have a photo album of the universe. The nearby galaxies show its adulthood, the moderate distances show its teenage years, and the farthest galaxies show its childhood. The ultimate in this time travel viewing is the cosmic microwave background, not a galaxy, but the afterglow of the Big Bang itself, which comes from a time about 380,000 years after the Big Bang. That light has taken 13.8 billion years to reach us, filling the universe with a faint microwave glow from every direction. It is the oldest light we can see, the edge of the observable universe in time. Beyond that, the universe was opaque. In a sense, the microwave background is like a blank foggy glass beyond which our time machine cannot directly peer with light. But right up against that glass, we are now detecting the faint images of the earliest galaxies that formed just a few 100 million years later. With the James Webb Space Telescope, astronomers have identified candidate galaxies at 13.2 or 13.3 billion years in the past, when the universe was only 500 to 600 million years old. These are tiny, dim smudges in the infrared, but they are enormously important, as they represent the dawn of galaxies, the first few generations of stars lighting up cosmic night. Gravitational lensing adds to our time machine's power. Massive clusters of galaxies can act as natural telescopes, magnifying and bending the light of galaxies behind them that are even farther away. By studying lensing clusters, we have glimpsed galaxies at times perhaps only 300 to 400 million years post-Big Bang, their light boosted by the gravitational lens. In those lensed images, we see the universe in its infancy, trying to form structure out of the primordial matter. Some of these galaxies are so young that they have not yet had time to build heavy elements. They may still be in the era of the universe's first stars, the long hypothesized population 3 stars. Time delay is not just a novelty, it's a fundamental tool for cosmology. We measure the universe's expansion history by comparing distances and redshifts, which are tied to look-back time. Observing supernovae and distant galaxies was how we discovered dark energy, as we saw earlier. Those supernovae acted as beacons from the past, telling us how the expansion rate then compared to now. Looking at galaxies from different eras also lets us witness sequences of events across cosmic time. We have, for instance, watched a distant supernova explode not once, but multiple times, due to gravitational lensing splitting its light into several paths with different travel times. So one image of the supernova appeared, then another image of the same supernova, delayed by a few years. In such cases, relativity and light travel time combine to create a truly cinematic effect, as if we could watch replayed moments of cosmic history, Even within a single galaxy, light travel time can play tricks over large scales. For instance, some galaxies have active nuclei that vary in brightness. The light from the nucleus might reach us before light from parts of an outer gas ring that reflect that outburst. So by the time we see a reflection in the ring, it's showing a past state of the nucleus, light echoes. Astronomers have used these light echoes within our own Milky Way and other galaxies to infer past bursts of activity. The phrase look-back time is commonly used. A galaxy has a look-back time of, say, 5 billion years, meaning we see it as it was 5 billion years ago. If that galaxy could see us, it would likewise see the Milky Way as it was 5 billion years ago, long before the Sun and Earth existed. In a very real sense, the universe we see is a mosaic of different epochs, all sharing the present sky. This realization adds a profound depth to our stargazing. The night sky is a time tapestry. The stars we see in the Milky Way are a mix of ages, but they're near enough that we see them essentially in their current state. For galaxies, however, distance translates to age. When we gaze at the Whirlpool galaxy, 30 million light-years away, we see it as it was when early mammals were scurrying underfoot of dinosaurs on Earth. When we study a galaxy in the Hubble ultra-deep field at 12 billion light-years, we observe a piece of the universe at an adolescent stage, forming new stars at a frenetic pace. Thus, astronomy is a unique historical science. We cannot touch galaxies or run experiments on them, but the universe has conveniently put their past within reach via the finite speed of light. We observe, record, and compare, effectively watching the film of cosmic evolution by gathering frames from various times. Over the past decades, we've assembled a fairly coherent narrative. Small, irregular galaxies in the early times merge and form larger structures. Star formation peaks about 3 to 4 billion years after the Big Bang, then gradually declines. Galaxies transition from blue and star forming to red and dead as fuel runs out. Large-scale structures grow under gravity, then the acceleration of expansion starts to spread them apart. Appreciating that looking far is looking back also instills a sense of the enormity of time. The photons hitting a telescope's detector from a distant galaxy began their journey before Earth had life, traveled across expanding space, avoiding absorption, and finally ended their long voyage in our instruments, delivering a message from a bygone era. When we detect those photons and reconstruct an image, we essentially resurrect an ancient moment and give it witness. In summary, every galaxy is not just a point in space, but a point in time. By observing galaxies at various distances, we cover a timeline of the universe. The deeper we look, the younger the universe appears. The concept of time travel in astronomy isn't science fiction. It's built into the fabric of reality. We can never travel to the past ourselves, but the past travels to us in the form of ancient light. This is how, bit by bit, we have come to understand the history of galaxies and the universe. It's an awe-inspiring fact. To behold a galaxy's light is to gaze into a deep well of time, to see a cosmic memory streaming through the darkness. Through those memories, we have pieced together the epic story of how the cosmos transformed from a hot, uniform glow to the magnificent bejeweled abyss of galaxies we see today. Darkness. Silence. In the beginning, there is emptiness, a void without time, without form. All is still. No stars, no light, not even a whisper of existence. Not even time flows, for time itself has not yet begun. This nothingness is poised on the brink of everything, a deep, primordial calm. The cosmos is holding its breath, the pause before the first heartbeat of creation. From this pregnant nothingness, a subtle vibration stirs. Not a sound. There is no air for sound, no ear to hear, but a tremor of potential. In the silent void, something is about to happen. An anticipation builds, a tension at the edge of becoming. It is the moment before creation, the last instant of absolute stillness, like the hush before a symphony's first note. Perhaps it begins with a tiny quantum fluctuation, a random flicker of energy in the otherwise featureless nothing. That is enough. The seed of everything is about to unfurl. Then, a sudden expansion, an awakening. In an infinitesimal flash, the void blossoms into being. The universe exhales its first breath, and space itself unfurls violently. There is no sound. There is no outside for sound to travel in. But if one could witness this birth, it would appear as an all-pervading eruption of space. The cosmos doesn't burst into an empty room. It creates room. Every point rushes away from every other. In that first timeless moment, the seed of everything expands from submicroscopic to cosmic dimensions. Space outraces light, not violating physics, for space itself is expanding, carrying matter and energy with it, faster than light can travel. One instant, all of existence is smaller than an atom. A heartbeat later, it's as large as a galaxy. This is the extraordinary inflation of the infant cosmos, an exponential surge that blows up the universe's size by an unimaginable factor. What was nothing becomes the foundation of all things. This is the birth of the cosmos, the Big Bang. Yet it's no ordinary explosion. It's a rapid flowering of space and time itself. In an instant, smaller than a heartbeat, the universe rushes outward. There is no center to this expansion. Every location moves away from every other. It's not an explosion in space, but an explosion of space. Before, there was no here or there. Now space-time itself unfolds from an initial state of infinite density. Time begins with this moment. Before the Big Bang, there was no before in any meaningful sense. The cosmic clock starts ticking with creation. The universe has opened its eyes. In that newborn state, everything is energy, unimaginably hot and dense. The universe is a blazing, seething fireball. Temperatures soar to trillions upon trillions of degrees. Matter, as we know it, cannot yet exist. The distinction between matter and radiation blurs. Instead, a brilliant quark-gluon plasma fills space, a fog of light and primordial particles intermixed. All the forces of nature are unified here in a single superforce. Gravity, electromagnetism, the strong and weak nuclear forces. Initially they are one, wrapped in the symmetry of the very early universe. As the universe expands and cools just slightly, this symmetry breaks. Like ice crystals forming in cooling water, the unified force fractures into four distinct forces. Gravity separates first. The gentle sculptor of space becomes its own force. The strong nuclear force splits off next, binding quarks into particles. The electroweak force remains combined a moment longer, then divides into the electromagnetic and weak forces. The cosmic symphony tunes its instruments. One fundamental note has become a four-part harmony. In the blinding hot fog, these transitions release tremendous energy and imprint subtle irregularities on the structure of the plasma. During this splitting of forces, the energy of the universe churns matter and antimatter into being. Particles condense from the energy, a churning sea of quarks and antiquarks, leptons and antileptons. Quarks pair up into protons and neutrons. Electrons zoom around. For every particle of matter, a twin antiparticle exists. They form and annihilate in rapid succession, maintaining a furious equilibrium. But as the universe cools, a slight imbalance emerges. By chance or necessity, matter gains a tiny edge. Perhaps out of 1 billion particle-antiparticle pairs, one extra particle of matter survives without a partner. When the rest annihilate each other in bursts of gamma radiation, that tiny surplus of matter remains. This infinitesimal asymmetry, on the order of 1 part in a billion, is enough to tip the scales. It is the reason something, matter, and not just light, fills the universe today. Those leftover protons, neutrons, and electrons, a cosmic handful of matter, will eventually coalesce into galaxies, stars, planets, and people. Already, the future is seeded in those minuscule differences. Even the early plasma carries imprints of random quantum fluctuations from inflation, slight density variations that will grow into galaxies and voids eons later. The universe is less than a second old, expanding and cooling rapidly. Quarks have locked into protons and neutrons. A seething quark-gluon plasma has given way to a swarm of hadrons, protons, neutrons, mesons. A slight surplus of protons and neutrons exists after most antimatter annihilates. In the next few moments, light atomic nuclei begin to form. About 1 second after the Big Bang, neutrinos, ghostly particles that rarely interact, decouple from the hot plasma and stream freely through space, carrying away a bit of energy. These neutrinos form a cosmic neutrino background. Trillions of them permeate every cubic centimeter of space even today, though with energies so low, their motions correspond to just a couple degrees above absolute zero temperature, that they are nearly impossible to detect. By the time the universe is about 3 minutes old, the temperature has fallen enough for nuclear fusion to occur on a cosmic scale. Protons slam into neutrons to build helium nuclei. For a brief period, the entire universe becomes a nuclear reactor, forging the first elements. Most neutrons pair with protons to make helium-4, 2 protons, 2 neutrons. A few protons remain single as hydrogen nuclei. In those first 3 minutes, the young cosmos produces about 25% helium by mass, 75% hydrogen, and only trace amounts of deuterium, lithium, and other light nuclei. This primordial nucleosynthesis sets the basic chemical recipe of the universe. After that point, as expansion dilutes the fire, the temperature drops too low for further fusion. The nuclear furnaces wink out. The elemental mix, mostly hydrogen and helium gas, now simply expands and cools with the universe. The stage is set for everything that comes next, using those simple ingredients. Still, no atoms exist yet. The matter is fully ionized, nuclei and electrons flying separately in a hot soup. The universe is a brilliant, opaque plasma of charged particles and photons. Light, photons, scatters incessantly off free electrons. It cannot travel freely. Imagine an extremely dense fog of light, so thick that any photon's path is a tiny zigzag between collisions. Space is filled with a white-hot glow, but this light is trapped, bumping around within the plasma. If there were some observer inside this early universe, they wouldn't be able to see in any direction. All would be a featureless, blinding brightness, every line of sight ending almost immediately in a sea of charged particles. The universe is opaque, like the interior of a star, with radiation and matter coupled tightly. Yet the universe continues to expand and cool. With each passing moment, the sea of plasma thins and its temperature drops. After about 380,000 years, a profound change occurs. The temperature falls to roughly 3000 K, cool enough for electrons to settle into orbits around nuclei. Protons capture electrons. Helium nuclei capture electrons. For the first time, stable neutral atoms form, mostly hydrogen atoms. This epoch is called recombination. It has 2 tremendous consequences. First, the previously trapped photons are suddenly free. Neutral atoms do not eagerly scatter visible light, so as soon as the electrons bind into atoms, the fog of the early universe clears. All at once, the photons that had been bouncing around are released to stream across the cosmos. The universe goes from opaque to transparent in a cosmic eye blink. It's as if an impenetrable mist has evaporated, revealing a vast space for light to travel. Second, the formation of atoms produces light of its own. A warm glow fills the universe as electrons settle into atomic orbits and emit photons. The entire young cosmos shines like a giant star for a brief moment. That flash of released radiation is the cosmic microwave background, CMB, the afterglow of the Big Bang. Those photons have been journeying for 13.8 billion years, stretching to longer wavelengths with the expansion of space. Today, the CMB is a faint, cool bath of microwaves about 2.7 K above absolute zero, detectable with sensitive radio antennas. It is the oldest light we can see, a baby picture of the universe covering the whole sky. But at the moment of recombination, it was an orange-white glow flooding everywhere. The universe had become transparent, and light, after ages of captivity, could finally cross the cosmos. After this release of light, a hush falls over the cosmos. The brilliant afterglow from recombination quickly dilates into the infrared and fades from human visible view as space expands. No new light sources shine yet, for no stars have formed. The universe enters a cosmic dark ages. The gas, mostly neutral hydrogen and helium, now fills space almost invisibly. If there were an observer at this time, they would be surrounded by darkness, with only the faint red diffuse glow of the receding CMB to keep them company, and even that would soon redshift into invisibility. The temperature of the background radiation slides down below the red-hot range into the infrared and radio. The neutral hydrogen gas pervading space emits only a feeble radio line at 21 centimeters wavelength when its atoms' spins flip, but otherwise it is dark. The cosmos is quiet and unilluminated, yet much is happening in the dark. The tiny variations in density left from earlier epochs, those 1 in 100,000 ripples, now begin to grow under gravity's influence. Slightly denser regions exert a stronger gravitational pull, drawing in nearby gas ever so subtly. The matter of the universe starts to gather into a web of filaments and clumps, though no one can see it yet. Over tens of millions of years, the invisible architecture of the cosmic web takes shape. Immense filaments of dark matter and gas contracting and knitting together, with denser knots at their intersections that will become the first galaxies. In these hidden cradles, gravity works slowly but relentlessly. Clouds of hydrogen gas shrink and compress. The universe is dark but not inactive. It is preparing. Like a long, starless night before the dawn, the Dark Ages set the stage for the first light of stars. And then, after perhaps 100 to 200 million years of darkness, there is light again. The cosmic dawn arrives quietly at first. Deep in one of the densest, coldest hydrogen clouds, gravity finally achieves what it's been trying to do. The gas at the center of the cloud grows so hot and dense that hydrogen atoms begin to fuse into helium. A new kind of fire ignites. A star is born. In that moment, for the first time since recombination, starlight shines in the universe. A pinpoint of brilliant light illuminates the surrounding space, carving through the darkness. This first star is likely enormous, dozens or even hundreds of times the mass of our Sun. Because without heavier elements, early gas clouds fragment into big pieces. It burns a fierce blue-white, millions of times brighter than the Sun, pouring ultraviolet rays into the gloom. In the vicinity of this newborn star, the perpetual night is ended. One by one, more stars flicker on in other contracting clouds. The first generation of stars, we call them population 3 stars, are born in small proto-galaxies, tiny infant galaxies, where the gas pooled most strongly. They cluster together in those dark matter halos, like a handful of candles kindling in a vast dark hall. These first stars live fast and die young. Being so massive, they exhaust their nuclear fuel in a few million years. But while they live, they dramatically transform their surroundings. Each massive star's intense ultraviolet light creates a bubble of ionized hydrogen around it, turning the gas back into plasma. At first, this bubble is local. Starlight is quickly absorbed by the nearby dense gas. But as more stars join the fray, the ionized zones expand. The once neutral universe is reionizing. Gradually, the light from these early stars and nascent galaxies of stars breaks apart the cosmic fog of hydrogen that pervades space. The dark intervening gas clouds that separated regions of the universe become increasingly transparent as they are ionized. Over the next several 100 million years, these growing bubbles of ionized gas merge and spread throughout space. By around 1 billion years after the Big Bang, most of the intergalactic hydrogen is reionized, split back into protons and electrons by the flood of ultraviolet starlight. The universe, which had been opaque to high-energy photons since recombination, is now mostly transparent across all wavelengths. The cosmic dark ages have fully ended. During this era, the first galaxies are taking shape. Initially, they are tiny dwarf galaxies, mere clumps of a few million stars, but gravity draws them together into larger assemblies. Small proto-galaxies merge to form bigger galaxies. The universe, once a nearly uniform glow, now becomes a tapestry of light and dark. Clusters of stars huddle into the first galaxies, which in turn group into clusters and chains. Over hundreds of millions of years, hierarchical growth builds ever grander structures. Some young galaxies are irregular or chaotic, distorted by frequent collisions. Others settle into rotating disks. Within a few billion years, majestic spiral galaxies, like our future Milky Way, appear, their pinwheel arms twinkling with billions of stars. Massive elliptical galaxies form from the mergers of smaller systems, becoming huge balls of aging stars. Galaxies congregate under their mutual gravity. They form groups and clusters, containing dozens to thousands of members. These clusters, in turn, are connected by filaments of matter, creating a vast cosmic web of structure. Everywhere, galaxies interact. When galaxies draw near, their mutual gravity can rip and morph them dramatically. Two spirals might collide and coalesce into a single, larger galaxy, often an elliptical. Smaller galaxies are gobbled up by larger ones, their stars assimilated into the bigger galaxy's halo. These collisions and mergers trigger bursts of star formation as gas clouds slam together and collapse. The universe is building big galaxies from smaller ones in a great cosmic construction project. One could think of galaxies as the cities of the cosmos, great collections of stars, gas, and dust, spanning tens of thousands of light years. In the young universe, these cities were rising everywhere and also joining into metropolitan areas, clusters, and superclusters. On the largest scales, matter is strung out in an intricate pattern, the cosmic web. Thin filaments of galaxies and diffuse gas stretch across hundreds of millions of light years, with massive clusters at their junctions and vast voids between them. Astronomers have mapped colossal structures, like the Sloan Great Wall, a filament of galaxies and clusters over 1 billion light-years long, and huge voids nearly as empty and as large. Up to scales of a few 100 million to 1 billion light-years, we see coherent structures, filaments, sheets, and voids. Beyond that, on the very largest scales, the universe becomes nearly uniform. These immense formations are among the largest coherent objects in existence. Clusters and superclusters of galaxies, strings of matter like celestial highways, each holding countless suns. Our own galaxy belongs to the local group, a small cluster within the Virgo supercluster, which is part of the even larger Laniakea supercluster. An enormous flow of galaxies converging toward a common center of gravity. The cosmic web's lattice of filaments and voids is the skeleton on which the universe's structure hangs. It formed from the slight density variations in the early universe, amplified by gravity over billions of years. Dark matter, the mysterious, invisible mass that neither emits nor absorbs light, provided the scaffolding. It clumped first, pulling ordinary matter, gas, into its gravitational wells to form galaxies. Dark matter is the unseen scaffolding of the cosmos. Though we cannot see it directly, it makes up the bulk of the universe's mass. It neither glows nor interacts with light. So as galaxies formed, dark matter shaped their growth invisibly. Every galaxy sits in a vast halo of dark matter, much larger and more massive than the visible galaxy itself. Clusters of galaxies are held together largely by dark matter's gravity. We know dark matter is there because of its gravitational influence. Stars at a galaxy's edge orbit faster than they should if only visible matter existed, and galaxies in clusters move as if an unseen glue is holding them. We also observe gravitational lensing. Light from distant objects is bent and distorted by massive invisible halos of dark matter along the way, creating rings and arcs of light that betray the presence of mass where we detect no stars. From these clues, we infer that dark matter forms filaments and halos that outline the cosmic web. It provided the gravitational wells that regular matter fell into. Without dark matter's guiding hand, the universe's evolution would have been very different. Stars and galaxies might have taken far longer to coalesce, or might not have clustered into the rich structures we see. Dark matter neither creates light nor blocks it. It simply gravitates. It is likely some new kind of elementary particle, or particles, that interact only weakly with normal matter. Decades of experiments have yet to capture a dark matter particle directly, keeping its nature a profound mystery. But its existence is beyond doubt from the cosmic structures it allowed to form. It binds galaxies together and shepherds clusters. It is the silent partner to all cosmic creation, the universe's hidden mass. While dark matter works behind the scenes to hold structures together, another influence grows to prominence that pushes structures apart: dark energy. For the first few billion years after the Big Bang, the universe's expansion was slowing down. Gravity was gradually tugging matter back, trying to rein in the expansion. Many scientists once thought that perhaps the expansion would eventually halt and reverse into a big crunch. But observations near the end of the 20th century shocked us. The expansion isn't slowing, it's speeding up. Starting a few billion years ago, when the universe was roughly 2/3 of its present age, the expansion rate began to increase. Distant galaxies are receding faster and faster as time goes on. Some mysterious form of energy permeating all of space is driving this accelerated expansion. We call it dark energy. Dark because it eludes direct detection and understanding. The simplest explanation is that dark energy is an intrinsic property of space itself, the cosmological constant that Einstein once hypothesized. In essence, empty space has a sort of latent energy that causes it to expand. Unlike matter, which thins out as space expands, dark energy's density remains constant, or nearly so, as space grows. So as the universe gets larger, the total dark energy increases and pushes ever harder. About 5 billion years after the Big Bang, dark energy's repulsion overtook gravity's attraction on the largest scales. Since then, the universe has been in an era of accelerated expansion. What does this mean for the future? It means that galaxies not bound together by their own gravity will drift farther and farther apart. In our own local group, the Milky Way and Andromeda and satellite galaxies are gravitationally bound and will still merge eventually. Dark energy doesn't disrupt that. But beyond our local group, distant galaxies are speeding away. Over tens of billions of years, they will recede beyond our horizon of visibility. Dark energy seems to be the dominant component of the universe now, about 70% of the total energy content. It has the effect of a small anti-gravity force, very weak on local scales but significant across the vastness of intergalactic space. The nature of dark energy is one of the biggest open questions in cosmology. We often call it by that name simply as a placeholder for whatever is causing the acceleration. It could be a constant energy of the vacuum, which theoretical physics can conceive of, though with puzzlingly different magnitudes than observed. Or it might be a dynamic field that changes over time. For now, all evidence points to it behaving like a constant, the cosmological constant. If that holds true indefinitely, the fate of the universe is a continued accelerated expansion. Over extremely long times, this leads to a heat death scenario. The universe will become colder, darker, and more dilute as eons pass. Star formation will eventually cease because usable gas is used up or driven out of galaxies. Existing stars will burn out one by one until none remain shining. Galaxies will spread so far apart that none can be seen from any other. For trillions of years, the only stars will be old embers like white dwarfs and neutron stars slowly cooling, and the occasional flare of matter accreting onto a black hole. In the far future, even black holes, which are initially the last vigorous energy sources through their slow hawking radiation, will evaporate into nothing on timescales of 67 years or more. As expansion continues, all remaining particles, mostly electrons, positrons, neutrinos, and light, thin out into a cold haze. For eons, black holes would be the main remnants of cosmic structure, emitting a faint hawking glow as they gradually lose mass. But eventually even those last embers of the universe will wink out. No usable energy remains to fuel processes. Entropy, disorder, is maximized. The universe will approach a state of total thermodynamic equilibrium. Essentially an infinite, nearly empty void at an extremely low temperature, with particles so spread out they rarely, if ever, meet. Time, in a sense, would lose its meaning because almost nothing happens. It is a quiet, desolate finale, the Big Freeze. Another possibility, more dramatic, is the Big Rip. If dark energy is not constant but instead grows stronger with time, imagine a form of dark energy that becomes increasingly repulsive. It could eventually overcome all forces that hold structures together. In this scenario, billions of years from now, galaxies would fly apart from their clusters at ever-increasing speed. Later, gravity within galaxies would be overpowered. Stars would drift away from galactic centers. Eventually, star systems would become unbound. Planets would wander off from stars. In the final moments before the Big Rip, even atomic nuclei and fundamental particles could be torn apart as space's expansion rate diverges toward infinity. Essentially, the universe would be ripped to shreds, every bond and structure bursting as the fabric of space itself stretches violently. This fate depends on the nature of dark energy. Specifically, it requires an equation of state parameter, sometimes called phantom energy. Current observations of dark energy are consistent with $1, a constant vacuum energy, so a Big Rip seems unlikely given the data, but our knowledge of dark energy is incomplete. If future evidence suggested dark energy might strengthen, the Big Rip scenario would become a serious concern for the very far future. It would be a cosmos dying in a final, all-consuming explosion of its structure, a literally tearing end to time and space. Alternatively, the acceleration we observe now might itself be a phase that eventually ends. If dark energy were to decay or reverse sign, turn attractive, in the far future, the expansion could slow and halt. Gravity could then start pulling everything back together. This is the Big Crunch scenario, essentially a symmetric reversal of the Big Bang. If the universe's density were high enough or dark energy somehow flipped, the expansion would break to a stop eons from now and then gradually begin to contract. Distant galaxies, now long invisible, would creep back into view as they rush towards us. Over incredibly long spans, all galaxies would begin merging and collapsing toward a common center. The night sky would grow ever brighter and hotter as more galaxies, and eventually all matter, crowd into a shrinking volume. Stars might ignite in a furious burst as gas clouds compress during the contraction. Ultimately, all galactic material would coalesce, temperatures skyrocketing until everything, every atom and photon, crunches into a hot, dense state, perhaps similar to the universe's birth. This could be an oscillatory universe, perhaps to rebound in another Big Bang, a big bounce. Currently,
the evidence doesn't favor a big crunch. Our universe's geometry and expansion indicate it will expand forever, and dark energy shows no sign of dissipating. But if some unforeseen physics intervened, a cyclic cosmos isn't impossible. It has a certain poetic appeal, the universe breathing in and out, eternally reborn. There is yet another subtle doomsday scenario, vacuum decay, sometimes nicknamed the Big Slurp. This relates to our understanding of quantum fields. It's conceivable that the ground state of our universe, the vacuum, is not truly stable. We might exist in a false vacuum, a local minimum of energy that could, via a quantum tunneling event, transition to a lower energy state, a true vacuum. If such a vacuum decay occurred, a bubble of the new vacuum would nucleate somewhere in the universe and then expand at nearly the speed of light. Inside that bubble, physics could be radically different. Fundamental constants, particle masses, and forces might take on new values. This bubble would annihilate anything it encounters as it rewrites space. Because it moves so fast, one wouldn't see it coming. One moment the world is as normal, the next, the bubble wall rushes past, and everything as we know it is transformed or destroyed instantly. It's a very exotic scenario, and most calculations suggest if our vacuum were prone to decay, it likely would have happened billions of years ago, or won't happen for trillions of years to come. It requires specific and uncertain conditions in particle physics, notably involving the Higgs field's potential. Current measurements of the Higgs boson hint our vacuum might be metastable on timescales vastly longer than the current age of the universe. So while vacuum decay is a physicist's worst-case ending, it's not something we lose sleep over. If it were to occur, it would be the ultimate wildcard end. The universe as we know it abruptly vanishes, replaced by something else entirely, with no warning or remnant. So, the universe's story may end in fire or in ice, in ripping apart, or in a quantum whisper, or perhaps in ways we cannot yet imagine. Each scenario is an ending written into the equations of cosmology, but which, if any, will come to pass, remains unknown. Our best guess, based on current knowledge, is an eternal expansion leading to heat death. Yet the cosmos has surprised us before. The acceleration by dark energy was unforeseen until observed. There may be new physics awaiting discovery that alters the final act. In truth, the ultimate fate of the universe is still a mystery, and it is fitting that here, the universe, through the thoughts of the conscious beings it produced, contemplates how it might end. It's as though the cosmos itself wonders about its finale, using small intelligences within it, like us, to explore the question. But whatever the end might be, it lies unimaginably far in the future. Right now, the universe is alive with galaxies, stars, and perhaps life. The story is ongoing, and we find ourselves in a chapter rich with possibility. Consciousness. Now we arrive at one of the most marvelous phenomena in the universe. Out of non-living matter, through the gradual work of complexity and evolution, awareness has emerged. How astonishing that, in a cosmos governed by impersonal physical laws, collections of atoms have developed the ability to contemplate those very laws, and to feel joy and sorrow, wonder and intent. With the appearance of life and mind, the universe has gained eyes to see itself and minds to reflect upon its nature. Tiny, fragile living beings on insignificant worlds gaze up and discover the fire of creation in the sky. In them, cosmic evolution has become self-aware. Life began, at least on one small planet, Earth, when chemicals assembled into self-replicating structures. Exactly how is still uncertain. It may have been a stroke of chance in a warm pond or deep-sea vent, or a gradual emergence aided by the planet's chemistry. But the basic ingredients were forged long beforehand. The carbon, oxygen, nitrogen, and other elements essential to life were synthesized in stars and scattered by supernovae. Earth formed from cosmic dust, enriched by those elements, and life's molecules drew upon that bounty. Water,
a molecule of hydrogen and oxygen common in space, became the medium for biology's experiments. Single-celled organisms arose over 3.5 billion years ago in Earth's ancient oceans. They were simple, lacking nuclei, yet they metabolized and reproduced, launching the great tree of evolution. For billions of years, life remained microbial. Those microbes transformed the planet. For instance, cyanobacteria flooded the atmosphere with oxygen. 2.5 billion years ago, an early example of life reshaping its environment. Complexity built gradually. Cells joined into colonies, then into multicellular organisms with specialized tissues. By around 540 million years ago, the Cambrian explosion, a dazzling variety of multicellular life forms filled the seas. Some ventured onto land, plants first, then animals. Life developed structures like eyes to sense light, limbs to move, brains to process information. Evolution, driven by natural selection, explored an astonishing design space, resulting in creatures from dinosaurs to dragonflies. Among the myriad life forms, one lineage, primates, produced a species with exceptional cognitive abilities. On Earth, that species is Homo sapiens, us. We are latecomers, arriving only a few 100,000 years ago. In that short time, we leveraged intelligence to alter the planet and peer into the cosmos. Through us, the universe has learned about its own origins. We discovered the cosmic microwave background, essentially, the universe's baby photo. We identified the chemical elements in the stars, the same elements found in our bodies, confirming our intimate connection to the cosmos. We've sent spacecraft to neighboring planets and listened for faint whispers of the universe, like gravitational waves from black holes merging billions of light years away. Humans are made of the universe's matter. The iron in our blood was forged in stars, the calcium in our bones in stellar explosions, the water in our cells likely delivered by ancient comets. And now that matter can think and learn. In us, the stardust has become self-aware. Are we alone in this? The cosmos is vast, and the conditions that gave rise to life on Earth may exist in countless other places. There are hundreds of billions of stars in our galaxy, and trillions of galaxies. Surely, Earth is not the only world where chemistry blossomed into biology. We have already discovered thousands of exoplanets orbiting other stars, some in habitats where liquid water, and thus Earth-like life, could exist. Organic molecules, the building blocks of life, are found in interstellar clouds and meteorites. It seems the universe is biased toward forming the ingredients of life wherever it can. Simple microbial life might be common. Perhaps in the subsurface oceans of icy moons in our own solar system, life has independently arisen. But intelligent, technologically capable life might be far rarer. After all, in Earth's 4.5 billion year history, only one species has attained the ability to send signals into space. If other civilizations had arisen frequently in our galaxy's 13 billion year history, we might expect that some would have spread or made their presence known. The silence of the stars, sometimes called the Fermi paradox, could mean many things. Maybe intelligent life is indeed very scarce, or maybe civilizations are short-lived, or perhaps they communicate in ways we haven't recognized, or simply the galaxy is so immense that our nearest intelligent neighbors are extremely far away. As of now, we simply don't know if we are alone. It is both exhilarating and humbling to realize that, for now, we are the universe's only known self-observers. That status imparts a sense of preciousness to consciousness, ours and that of any other beings that may exist. Consciousness itself remains a mystery. How does the coordinated firing of neurons give rise to subjective experience, to the feeling of I am? This is the hard problem of consciousness that neuroscientists and philosophers grapple with. From the cosmic perspective, one can speculate. Perhaps consciousness is an emergent property when matter organizes in very complex ways, like in a brain. Or maybe there is some fundamental aspect of nature that includes mind. Some suggest even elementary particles might have proto-conscious qualities, an idea called panpsychism. If the latter were true, then as the universe became more complex, consciousness gradually woke up, more fully within it. If the former is true, then consciousness is an exceedingly rare cosmic phenomenon, requiring a fortuitous chain of events and structures, like brains, to exist. Either way, consciousness is a way in which the universe, otherwise governed by simple physics, has something internal, something it feels. Through conscious beings, the universe experiences qualities like color, sound, pain, and love, which otherwise would not exist. A rock orbiting a star doesn't know it's in orbit. A star doesn't know it's shining. But we, conscious entities, do know and appreciate these things. Our minds can hold models of stars and galaxies. In a sense, tiny portions of the universe, our minds, have become reflective, able to contemplate the whole. Consciousness also allows the universe to ask questions about meaning and purpose. Questions that in a purely material sense might be moot, yet that matter deeply to the conscious creatures themselves. We, for instance, seek purpose in our small lives amid this vast cosmos. Science tells us how we came to be. It doesn't tell us why, if there is a why. Many thinkers suspect that questions like, why does the universe exist? Or, what is the purpose of consciousness? May not have answers in the way we hope. The universe might just be, without deliberate purpose. Yet here we are, imbued with love, curiosity, and longing for meaning. In a way, one might say the universe's purpose, if any, is what we, as parts of the universe, make of it. By our very nature, we invest the cosmos with meaning. When we create art, discover scientific truths, show kindness to one another, those acts give the universe experiences it would not otherwise have. Through us, the cold equations of physics bloom into poetry and empathy. Through us, the universe can admire itself and say, it is beautiful. We humans, so small and temporary, are a way for the cosmos to know itself. We are aware that we are made of star stuff and that we live on a mote of dust suspended in a sunbeam, to borrow a phrase. We've also realized that our minds are the result of billions of years of cosmic and biological evolution, a precious, transient flicker in a very old and vast space. Each of us is a tiny fragment of the universe that for a brief moment is self-aware. And we carry the heritage of the entire cosmos within us. Consider the atoms in your body. The hydrogen in your drinking water was made in the first minutes after the Big Bang. The carbon in your cells was forged in some star billions of years ago. The calcium in your bones was fused in the heart of a massive star and scattered in a supernova. The iron in your blood came from the violent death of a star. The phosphorus enabling your DNA was built in cosmic furnaces as well. We literally embody cosmic history. Stardust runs through our veins. When we look up at the night sky, we are gazing at our kin. The stars are our distant cousins, related by common origin in the Big Bang. The light that reaches our eyes triggers thoughts in our brain, a star's photons, causing a pattern of electrical signals in a mammal's nervous system. How extraordinary that a thermonuclear reactor, millions of light years away, can set off a spark of thought in a being on Earth. Through those thoughts, the universe is, in a small way, conscious of itself. In fact, when you consider it deeply, there is no sharp separation between us and the universe. We are not observers outside the cosmos. We are an integral part of it. Our bodies are composed of the universe's matter. Our thoughts arise from physical processes in our brains that obey the universe's laws. We emerged from this cosmic system and are immersed in it completely. The universe is our larger body, and we are like its tiny self-aware cells. At this point in the story, the universe, through human minds,
can even attempt to summarize its own journey. In doing so, it turns the mirror on itself. We, on our pale blue dot, have reconstructed much of cosmic history. We have mapped the afterglow of the Big Bang. We have observed galaxies across cosmic time and seen back to when the first stars were kindling. We've understood how elements were born in stars and how Earth came to be enriched by them. In short, we have become the historians of the universe, cataloging its saga. And we are the universe's storytellers too, giving narrative and meaning to events that on their own are neither good nor bad. They simply are. The rise of life, the collapse of a star into a black hole, these just happen, but through conscious eyes, they become stories of wonder, tragedy, and transformation. Now, having journeyed from the beginning of time to speculations about the end, and from the simplest particles to conscious beings, let us conclude with a moment of reflection. Take a slow breath. Feel your lungs fill with air. Much of that air was once inside of stars and will be part of other life after you. Feel your heart beating, a rhythm that connects you to the first heartbeat of the cosmos when it expanded from silence. In this very moment, you are the product of the entire history we've recounted. You are ancient hydrogen and stardust shaped by gravity and chemistry, given form by biological evolution, and endowed with a spark of awareness. The silence that we imagined at the very beginning still echoes within you in the quiet moments between your heartbeats. The darkness that once enveloped the cosmos is the same darkness behind your closed eyelids when you contemplate. But now the silence is filled with the potential for thought, and the darkness can be lit by the imagination. Stardust remembers. The atoms of your body hold memory, not conscious memory, but the record of cosmic events encoded in their existence. Each heavy element remembers a star that lived and died. In a way, when you think about the universe is remembering itself. Your brain's atoms clicking into patterns that mirror the cosmos outside. Time flows through us. We are part of the grand progression of entropy and evolution. The arrow of time that began at the Big Bang runs through every cell in our body. The blood circulating in your veins right now was forged in a sequence of events going back to the beginning of time. You are a wave traveling through the ocean of time, temporarily taking shape as an individual crest before merging back. The universe is not far. It is here. It is in your breath, in your bones, in the light that falls on your eyes. It is the ground beneath you and the space around you. We carry the universe within us, and we walk within the universe. There is no separation. The cosmos is our home and our essence. When the universe speaks, through equations or photons, we can understand because we too are expressions of those same underlying laws. When we cry out in joy or despair, that is the universe, in a small part of itself, experiencing emotion. Our narrative nears its end, but the universe's narrative continues, unfinished. The story of the cosmos is still being written, in the motions of galaxies, in the birth of new stars, and perhaps in the endeavors of conscious beings like us. We find ourselves at a wondrous juncture. We can look back and reconstruct much of cosmic history, and we can look forward and ponder cosmic futures, but we are still at the dawn of understanding. There remain deep mysteries, dark matter, dark energy, the origin of it all, the purpose of consciousness, that we have yet to unravel. The universe is unfinished, not just in the temporal sense, with events yet to happen, but in the sense that its truth is not yet fully known. There are pages left to read, and perhaps new pages still to be written by the acts of intelligences. If we last long enough to spread life beyond Earth, for example, we will be adding a new chapter to the universe's story. We end where we began, in darkness and stillness. Picture the void before creation once more, that expectant nothingness. Picture the stillness after a possible end, the quiet of a heat-dead cosmos,
or the silence of a post-Big Crunch void. In some sense, they are the same silence. The universe may end in silence as it began in silence. But between those two silences, what a symphony of being has played out. A symphony with movements of blazing brilliance, the era of stars, and deep recesses of melancholy, the cold depths of space, with themes that intertwine matter and energy, creation and destruction, simplicity and complexity. We have been part of that symphony, a brief, delicate violin solo in a grand orchestra. Without us, it would still be magnificent, but with us, it can be appreciated from within. We are the universe listening to its own music, even as we play our small part. The narrative pauses now, but it does not truly stop. Even as these words cease, stars will continue to shine and atoms will continue to collide in the vast reaches of space. The universe goes on, ever unfolding. And you, a child of the stars, go on as well, carrying the knowledge and awe gleaned from this story. When you next step outside on a clear night, perhaps you will feel more connected to those distant points of light, knowing what they are and how they came to be. Perhaps you will sense, as ancient stargazers did, that the universe is not a cold stranger, but a deeply related entity, our ancestor, our substance, our home. Listen, in the quiet night, under the cosmic ocean of stars, you can almost hear it, the heartbeat of the universe. It is the blood pulsing in your ears, and the echo of gravitations and vibrations that ripple through space. It is the memory of the Big Bang imprinted in your very atoms, and the faint music of all the stars carrying on through the dark. In that soundless music is a truth felt if rarely spoken. The universe is alive in us, and we are alive in the universe. We are not mere observers, we are participants. Its story is our story. Its beginning is our beginning, and its future, though unknown, is tied to us as well, for we are part of this cosmos. The tale of the universe is thus far a tale with no known ending, an unfinished book, an open-ended quest. We find ourselves on one shining page of that epic, aware of our role and eager to read on. The universe is, forever, unfinished, an ever-unfolding mystery in which we, for a fleeting moment, get to partake. And in that fact lies profound hope and meaning. The song of the universe goes on, and we, conscious flecks of stardust, get to harmonize with it, adding our verse to the cosmic chorus. The story continues, and we are part of it, always. It is unfinished.